Duvid here. We are live, week in review. So this episode 8 since Jennifer, since I've been taking this solo. So God bless Jennifer, and hope she's making progress in whatever she's doing. But keeping week in review going. So an interesting week. Let me jump right in and share some of these links just to get them off the stream. I might go slightly shorter this week, 2-3 hours as opposed to the usual 5-6 hours, because I didn't accomplish that much this week because of Shavuos, and I was pretty busy doing other work, so I didn't prepare particularly that much research this week. So I was just watching this interesting modern MBA on Starbucks must crush union to survive, an in-depth overview of the history and business model of Starbucks. Duvid has, over my lifetime, spent thousands and thousands of dollars at Starbucks for periods of my life. I went to Starbucks almost every day. Sometimes in my life, like University of Michigan, I would go to Starbucks even like twice a day. And now I have, like, Duvid, this is a Starbucks iced coffee. So I usually keep Starbucks iced coffee in my refrigerator, but only go to Starbucks a few times a month now. Since COVID-19, stopped going to Starbucks. So like it was largely COVID-19 that got me away from going to Starbucks. So till then, for years, I'd always went. So here was news this week. There are a few different articles on this. So most of them are talking about Neuralink, the Elon Musk's brain communication interface device. So CNBC was reporting a competitor, so the FDA granted trials for human trials on the chips for human computer brain interface devices, most famous through Elon Musk's Neuralink brain computer interface. However, there are other companies also that also have gotten the same parodromics. So I hadn't really heard of parodromics, but so Neuralink got the FDA approval starting this week in parodromics. Another company also got their FDA approval, so we'll see what happens with that. Should be interesting advances in the chips, getting chips into our brain. So it's here. The FDA approvals came, and so keep you informed about what's going on with that. This was interesting. A new AI, not ChatGPT. ChatGPT is just the more popular version, but a new form of AI related to DeepMind and AlphaZero, AlphaGo has discovered a new method of doing matrix multiplication. So forget the name, the common method of matrix multiplication for like the last 50 years, Strasson's algorithm. So I don't have Jennifer here to my math expert, but there's some Strasson's algorithm is the mainstream method for doing matrix multiplication, and DeepMind's AlphaZero program has just came up with a new tensor mathematical method for matrix multiplication. So pretty interesting. I didn't prepare that much in depth about it. See if the article has anything of note to share. AI reveals new possibilities in matrix multiplication. Mathematicians love a good puzzle. So the standard algorithm is Strasson's algorithm. And so unfortunately, I didn't research this enough to really go on. I'm not even that familiar with Strasson's algorithm. let alone this new algorithm. But I thought it's interesting, and so it is, DeepMind, the same program from AlphaZero, from chess. Speaking of chess, here was a new study on book moves from chess. So when does a chess player experience a new move on average? And so, interesting that most players will play a new move by the sixth move in chess. And relatively, there's a huge number of possibilities. So it's not that surprising. Even in many cases, there'll be a new move on like move 2 or 3. And, by move 4, there's so many possibilities that many chess games have a new move already by move 3. And by move 6, the majority of chess games have a new move. And a rating distribution is actually stronger players that would tend to see a newer move delayed till later. So it's just a little interesting data study here on Lichess. God forbid, the Bilderberg meeting was this last week, and when following the Bilderbergers. So I haven't really followed the Bilderbergers the last few years. They're still around. They're still powerful. Although, it would appear that there's other more powerful groups, more powerful organizations than the Bilderbergers. But Max Blumenfeld was on the Hill breaking down, kind of what's going on with the Bilderbergs, showing, some of the directions of globalism and, modern news, Henry Kissinger, Google, international technology. But Bilderberg is more European-centric, although many of the global players and American entrepreneurs are involved. It's more Eurocentric, and the power of Europe has been decreasing. But you did have the Bilderbergers meeting just this last week. Detroit, God forbid, is no longer the largest majority black city. Memphis, Tennessee has surpassed Detroit as the largest African American city in you see 1980 there was the population in Detroit has declined to under 600,000, as where Memphis has been holding steady in the 600,000s, and Detroit's decline has now went under the population of Memphis. Although Detroit has a 76% black population, Memphis has a 63% black population. But so Detroit for a long time had been the largest black majority population in America, and now it is finally went under that of Memphis, Tennessee. So God bless Memphis, Tennessee. So I was following these latest, the Bhaktivedanta Institute for Higher Studies, the Hare Krishna, Vedic science think tank. And so I've been watching their videos, a little talking with some of the devotees on a Facebook feed. And they have a new series on Richard Thompson, Sataputta, mechanistic and non-mechanistic science. So great book. And so they're talking about that. And little Ashish Dallela, and he used to be part of this, but I guess he had beef and personality issues and wasn't able to get along with the people in the Bhakti Vedanta Institute for Higher Studies. I was listening to the lecture of Hiri Dayananda Goswami talking about the philosophy of science, and so it was an interesting topic. We need more philosophy of science. Asia Metri had a recent video on the Shaw Brothers. Duvid took a class in Stony Brook on the Chinese martial arts films, and used to really like Chinese martial arts films. And my roommate, Slang Mang Brown, the rapper I used to manage, work together with, he was a big fan of Shaw Brother movies, and So just a little history of the Shaw brothers, who I guess have used their money to move into other businesses. So a little bit interesting. In Jewish news, the conservative movement has allowed the use of vegetarian and vegan without a hechsher. Sometimes there could be a little question with the oil, but they've moved completely to allowing vegetarians. I know they had, the local in season. There'd been Rabbi Jason Miller near me, who has a hechsher, and they're asking, is it worth getting the hechsher? I told him it probably didn't mean that much, because most Orthodox Jews wouldn't eat there even with the hechsher, and the people that would eat there would probably eat there even without the hechsher. So here you have that at this point, the conservative movement ruling vegan and vegetarian restaurants don't even need a hechsher. So Duvid is a big frequenter of vegan and vegetarian restaurants. I think Veg Fest at Eastern Market. My mom was just telling me about that. So Veg Fest Eastern Market will be next Sunday. Maybe I'll stream a little bit, a little like a ramble, and so Duvid vegetarian for years now. So the Veg Fest here at 100 vendors ready to eat. So as you could see, so good move on the Conservative Association. God forbid, Andrew Tate's view on women. YouGov in the UK survey about the popularity of Andrew Tate and how people in the UK feel about the opinions of Andrew Tate. And you could see of 93% of younger men have heard of Andrew Tate. Of all Britons, you see the favorability rate is relatively small, but over a quarter of younger Britons have a favorable view of Andrew Tate, or slightly more favorable. The older Britons, much less so. You could see still vastly unfavorable, although among younger men, Andrew Tate's polling numbers are much higher. You can see there in the purple. So just random. Okay, so let me take it off screen share for a second. I've had these here for a few weeks, and I'm going to take them to my dad's. I keep on forgetting to show them. So I got these great courses a while back, and I've been meaning to show them for over a month now. So let me just show these. So new great courses: Americans' Great Trails, Wondrium, Assessing America's National Security Threats, H.R. McMaster's course. And I generally watch the good fellows at the Hoover Institute. So H.R. McMaster, I think he's been in the Trump administration. Now he's at Hoover. And National Security Advisor, Lieutenant General, now at the Hoover Institute. So he made a course for Wondrium, Assessing America's National Security Threats. This one was pretty interesting. Banned books, burned books, forbidden literary works. A history of banning books, starting back with Ulysses and some older ones, Allen Ginsberg, to modern day textbook wars and critical race theory. So all over, all sorts of different books for different reasons being banned. Pretty comprehensive history, not particularly political, leaning one direction, more academic. Professor at Georgetown. Creation stories of the ancient world. This was pretty interesting. One of the critics said should be creation stories of the Middle Eastern ancient world, but overview of quite a few of the ancient creation stories, mostly from the Middle East. Discovering West Africa, Ghana, Senegal, and Cameroon. So, pretty interesting. Just, modern day. Actually, some of these areas are reasonably wealthy and well developed. They have like a huge statue, bigger than the Statue of Liberty, in I think Senegal, and interesting historical sites. God forbid some of the remnants of slavery from hundreds of years ago, but also modern Africa. So it was pretty interesting. I've watched most of these already. Epigenetics, how environment changes your biology. This one was also pretty interesting. Epigenetics, an important topic. Macroeconomics made clear. So always good to refreshing your learning. So a new course on macroeconomics, introduction. This one was pretty interesting too. A pastime of their own. The story of the Negro Baseball League, American history. Came out, I guess, Black History Month. So I listened to most of these already on my online subscription. So these are new and sealed. But here is the real ancient Egypt from various professors. New wisdom or academic studies on ancient Egypt. Storytelling in the human condition. Also, generally interesting. A. Mark Smith, thanks for tuning in. God bless. And understanding cognitive biases. This one, kind of basic, a topic that we've covered on Week in Review many times. So just interesting things. So I've had these over a month. I'm going to take them to my dad's house, and I keep on forgetting to show them on Week in Review. So let me enter back screen share. So God forbid some small viewership here. That's okay. We'll pound through and hope anyone tuning in enjoys. So last week I covered I eulogized my friend Jean-Louis Bourgeois, who had passed away a few months ago. And I'm not doing too much streaming, these days. I'm not really involved in too many, various streams or different things. So hopefully we'll keep Week in Review interesting, but minimally, do it. I'm doing my research, so I'll just share my research. So the Science of Consciousness conference this week just finished. Duvid had wanted to, wait more for. Thanks for tuning in. So I'd wanted to go to the Science of Consciousness conference and wasn't able to. It was too much for me to figure out how to get there and pay for it. And so here is some iCloud pictures from various presenters there. Here's Brad Caldwell. Hey, Michael, if you want to talk a little bit, I'm going to read a paper. I don't have that much, but if you want to talk, share how your Shavuos was. So let me make Michael a moderator there and add the StreamYard link. So I have one paper. It's actually pretty long. I want to read through. But if you want to pop on and talk about your Shavuos or anything, Michael, that's fine. We also went to the How Can I Say for Torah? That was already last week. I shared that last week. So here you can see some slides of various presenters. Brad Caldwell, so appreciate he posted some pictures. I noticed Stuart Hameroff, there wasn't much information. I couldn't find a single news story. The Science of Consciousness, not particularly that interesting. And I guess there was this little spat between Philip Ball and Stuart Hameroff, where someone had been claiming that Stuart Hameroff and his theory that some of these new tests are disproving orchestrated objective reduction. I'm going to do an overview of the quantum theories of mind today. So that's the main paper I'm going to be reading through. I shared last week, but I'm going to try to read through this whole paper this week. They'll have a complete overview of the various theories. So you can see a little bit of Quantum Magazine here. Let me read a little bit from this was actually a little bit ago, and then there was the reply from Hameroff. So there was a little Twitter feud questioning the current status of collapse theories. So this already goes back to October of last year. I didn't notice this when it came out. So let's look at the experiments. Spell doom for decades-old explanations of quantum weirdness. Physical collapse theories have long offered a natural solution to the central mystery of the quantum world, but a series of increasingly precise measurements are making them untenable. How does objective reality emerge from the palette of possibilities supplied by quantum mechanics? That questions the deepest and most vexed issue posed by the theory is still the subject of arguments a century old. Possible explanations for how observation of the world yield definite classical results drawing on a different interpretation of what quantum mechanics mean have only multiplied over those 100 or so years. But now we may be ready to eliminate at least one set of proposals. Recent experiments have mobilized the extreme sensitivity of particle physics instruments to test the idea that the collapse of quantum possibilities into a single classical reality is not just a mathematical convenience, but a real physical process, an idea called physical collapse. The experiments find no evidence of the effects predicated by at least the simplest varieties of these collapse models. It is still too early to say definitely that their physical collapse does not occur. Some researchers believe that the models could yield yet be modified to escape the constraints placed on them by the experiment's null results. But while it is possible to rescue any model, said Sandro Donati, a theoretical physicist at the National Institute for Nuclear Physics in Italy, who led one of the experiments, he doubts that the community will keep modifying the models indefinitely, since there will not be too much to learn by doing that. The noose seems to be tightening on the attempt to resolve the biggest mystery of quantum theory. What causes collapse? Physical collapse models aim to resolve the central dilemma of conventional quantum theory. In 1928, Erwin Schrödinger asserted that a quantum object is described by a mathematical entity called a wave function, which encapsulates all that can be said about the object and its property. As the name implies, a wave function describes a kind of wave, but not a physical one, rather is a probability wave, which allows us to predict the various possible outcomes of measurements made on the object and the chance of observing any one of them in a given experiment. If many instruments are made on such objects, when they're prepared in an identical manner, the wave function always correctly predicts the statistical distribution of outcomes, but there is no way of knowing what the outcome of any single measurement will be. Quantum mechanics offers only probabilities. What determines specific observations? In 1932, the mathematical physicist John von Neumann proposed that when an instrument is made, the wave function is collapsed into one of the possible outcomes. The process is essentially random, biased by the probabilities it encodes. Quantum mechanics itself doesn't appear to predict the collapse, which has to be manually added to the calculations. An ad hoc mathematical trick, it works well enough, but it seemed and continues to seem to some researchers to be an unsatisfactory sleight of hand. Einstein famously likened it to God playing dice to decide what becomes real. what we actually observe in our classical world. The Danish physicist Niels Bohr, in his so-called Copenhagen interpretation, simply pronounced the issue out of bounds, saying that physicists just had to accept a fundamental distinction between the quantum and the classical regimes. In contrast, in 1957, the physicist Hugh Everett asserted that wave function collapse is just an illusion. In fact, all outcomes are realized in near infinite number of branching universes, what physicists now call many worlds. The truth is that the fundamental cause of the wave function collapse is yet unknown, said Inwook Kim, a physicist at the Lawrence Livermore National Laboratory in California. Why and how does it occur? In 1986, the Italian physicist Giancarlo Ghirardi, Albert Ramini, and Tullio Weber suggested an answer. What if they said Schrodinger's wave equation was not the whole story? They posited the quantum system is constantly prodded by some unknown influence that can induce it to spontaneously jump into one of the system's possible observable states on a timescale that depends on how big the system is. A small isolated system, such as an atom in a quantum superposition, a state in which several measurement outcomes are possible, will stay that way for a very long time, but bigger objects, a cat, say, or an atom, when it interacts with macroscopic measurement device, collapse into the well-defined classical state almost instantaneously. This so-called the GRW model, after the trio's initial, was the first physical collapse model. A later refinement known as the continuous spontaneous localization model involved gradual continuous collapse rather than a sudden jump. These models are not so much interpretations of quantum mechanics as additions to it, said the physicist Magdalena Zich of the University of Queensland in Australia. What is it that causes the spontaneous localization via wave function collapse? The GRW and CSL models don't say. They just suggest adding a mathematical term to the Schrodinger equation to describe it. By the 1980s and the 1990s, the mathematical physicist Roger Penrose of the University of Oxford and Lajos Diasi of Eötvös Loránd University in Budapest independently proposed a possible cause of the collapse: gravity. Loosely speaking, their idea was that if a quantum object is in a superposition of locations, each position state will feel the others via their gravitational interaction. It is if their attraction causes the object to measure itself, forcing a collapse. Or if you look at it from the perspective of general relativity, which describes gravity, a superposition of localities deforms the fabric of spacetime in two different ways at once, a circumstance that general relativity can't accommodate. As Penrose has put it, it is a standoff between quantum mechanics and general relativity. Quantum will crack first. The test of truth. These ideas have always been highly speculative, but in contrast to explanations of quantum mechanics like the Copenhagen and Everett interpretation, physical collapse models have the virtue of making observable predictions and thus being testable and falsifiable. If there is indeed a background perturbation that provokes quantum collapse, whether it comes from gravitational effect or something else, then all particles will be continuously interacting with this perturbation, whether they are in superposition or not. The consequence should, in principle, be detectable. The interaction should create a permanent zigzagging of particles in space comparable to Brownian motion, said Catalina Corsiano, a physicist at INFN. Current physical collapse models suggest that this diffusive motion is only very slight. Nonetheless, if a particle is electrically charged, the motion will generate electromagnetic radiation in a process called Bremsstrahlung. A lump of matter should thus continually emit a very faint stream of photons, which typical versions of the model predict to be in the X-ray range. Donati and his colleague Bassi have shown that the emission of such radiation is expected from any model of a dynamic spontaneous collapse, including the Diasi-Penrose model. Yet, while the idea is simple in practice, the test is not so easy, said Kim. The predicted signal is extremely weak, which means that the experiment must involve an enormous number of charged particles to get a detectable signal, and the background noise which comes from sources such as cosmic rays and radiation in the environment must be kept low. Those conditions can only be satisfied by the most extremely sensitive equipment, such as those designed to detect dark matter signals or the elusive particles called neutrinos. In 1996, Quijufu of Hamilton College in New York, then just an undergraduate, proposed using germanium-based neutrino experiments to detect CSL signature of X-ray emission. Weeks after he submitted his paper, he was struck by lightning on a hiking trip to Utah and killed, God forbid. The idea was that the protons and electrons in germanium should emit the spontaneous radiation, which ultrasensitive detectors would pick up, yet only recently have instruments with the required sensitivity come online. In 2020, a team in Italy, including Donati, Bassi, and Corcorino, along with Diassi in Hungary, used a germanium detector of this sort to test the Diassi-Penrose model. The detectors created for a neutrino experiment called IJEX are shielded from radiation by virtue of their location underneath Gran Sasso, a mountain in the Apennine Range in Italy. After carefully subtracting the remaining background signal, mostly neuroradioactivity from the rock, the physicists saw no emission at a sensitivity level that ruled out the simplest form of the Diassi-Penrose model. They also placed strong bonds of their parameters within which various CSL models might still work. The original GR model lies just within this tight window. It survived by a whisker. In a paper published this August, the 2020 result was confirmed and strengthened by an experiment called the Majorano demonstrator, which was established primarily to search for the hypothetical particles called Majorano neutrinos, which have the curious property of being their own antiparticles. The experiment is housed in the Sanford Underground Research Facility, which lies almost 5,000 feet underground in a former gold mine in South Dakota. It is a larger array of high-purity germanium detectors than IJEX, and they can detect X-rays down to low energies. Our limits is much more stringent compared to the previous work, said Kim, a member of the team. Messy end. Although physical collapse models are badly ailing, they're not quite dead. The various models make very different assumptions about the nature of the properties of collapse, said Kim. Experimental tests have now excluded most plausible possibilities of these values, but there's still a small island of hope. Continuous spontaneous localization models propose that the physical entity perturbing the wave function in some sort of noise field, which the current tests assume is white noise uniform at all frequencies. That is the simplest assumption, but it's not possible that the noise might be colored, for example, by having some high-frequency cutoff. Koruenu said that the testing these more complicated models will require measuring the emission spectrum of higher energies than has been possible so far. The Majorana demonstrator experiment is now winding down, but the team is forming a new collaboration with the experiment called Gerda, based in Gran Sasso, to create another experiment probing neutrino mass called Legend. It will have more massive and thus more sensitive germanium detector arrays. Legend may be able to push the limits of CSL models further, said Kim. These are all also proposals for testing these models in space-based experiments which won't suffer from noise produced by environmental vibrations. Falsification is hard work and rarely reaches a tidy end point. Even now, according to Roger Penrose, who was awarded the 2020 Nobel Prize in Physics for his work on general relativity, is working on a version of the Diassi-Penrose model in which there's no spontaneous radiation at all. All the same, some suspect that for this view of quantum mechanics, the writing is on the wall. What we need to do is rethink what these models trying to achieve, said Zich, and see if the motivational problems may not have better answers through a different approach. Well, if you argue that the measurement problem is no longer an issue, we have also learned much in the years since the first collapse models were proposed about what quantum measurements entail. I think we need to go back to the question of what these models were created for decades ago, she said, and take seriously what we have learned in the meantime. And so let me just read this gloss here on quantum consciousness. One of the most provocative and speculative predictions of the Diassi-Penrose physical collapse model is that it might explain consciousness. Specifically, gravity might induce the collapse of quantum mechanical vibrations in protein filaments called microtubules and neurons, thereby triggering conscious awareness. These ideas, which Roger Penrose developed in collaboration with anesthesiologist Stuart Hameroff, produced the Orch OR model of consciousness. If physical collapse models are excluded by experiments, as they seem to be, then the game is up. The model cannot possibly explain consciousness. Regardless, other experiments seem to be putting an end to the Orch OR anyways. The oncologist and physicist Jack Tosinski of the University of Alberta is heading a project with Hameroff in which several teams have independently conducted biophysical experiments on aspects of the model, including spectroscopic studies of the collective quantum states of microtubules. The report is still in the peer review, but the results showed no sign of the effects predicted. Nothing is conclusively ruled out yet, if it ever can be, but the improbability of each Orch OR assumption becomes compounded when taken in combination, which makes it exceedingly hard to accept such an infinitesimally small probability. Okay, so let's look at another article. This is Stuart Hameroff's reply to the smear campaign at the crossroads of consciousness and space-time geometry. Comment on At the Crossroads, the Search for Spontaneous Radiation in the OR Consciousness Theory by Dirk. So that was just the Science the popular article about. So I don't know if Mark, if the stream slowed down for a minute. Hopefully it's working now. So I apologize about that, but hope it's working now. Okay, introduction, A Tale of Two Orchestrated Reductions. The Crossroads article, a preceding paper in Nature Physics, and a press release by the think tank FQXI wrongly insinuate the Penrose-Hameroff OR theory of consciousness and the Penrose orchestrated reduction on which it is based are refuted. In OR, quantum superpositions are entangled microtubules inside brain neurons are orchestrated while reaching threshold for Penrose objective reduction, causing instantaneous wave function collapse, selections of classical microtubule states, and moments of orchestrated conscious experiments. Roger Penrose used Einstein's general relativity to equate quantum particles with tiny spacetime curvatures and superpositions with tiny spacetime curvature separations. These would be unstable and undergo quantum state reduction, collapse of the wave function at an objective threshold, objective reduction, generating new states of classical reality, and fundamental unitary moments of conscious experiments, or qualia. Penrose orchestrated objective reduction is unique, bold, and logical, there being no more cogent nor specific proposal regarding consciousness in all of science. Penrose objective reduction and orchestrated objective reduction are proposed to occur due to the objective threshold at the average time where h is the Planck-Dirac constant of this time equals h divided by E, and E is the gravitational self-energy of the superposition. A similar version of OR, but without consciousness, was introduced by Hungarian physicist Lajos Deasi, an investigator and author on reference. But Penrose orchestrated reduction and Deasi orchestrated reduction proposed reduction at time t equals h divided by eq, and consequently Penrose orchestrated objective reduction and Deasi objective reduction are often lumped together as DP theory, but the Deasi predicts measurable radiation with each reduction event, and the Penrose does not. Penrose predicts proto-conscious qualia, the experiential components of full orchestrated consciousness, and the Deasi does not. An elegant experiment was performed to look for Deasi radiation in a germanium crystal under Gran Sasso Mountain in Italy, but continuous monitoring over 2 months did not find any spontaneous related reduction radiation. Deasi appeared to be ruled out, and Penrose validated, but the authors remained committed to Deasi radiation and launched a literal smear campaign to justify its absence, the big smear. In Nature Physics, Donati say, we then report the results of a dedicated experiment at the Gran Sasso Underground Laboratory to measure this radiation emission rate, but they did not then report the negative result. Rather, they pivoted to our results at a lower bound on the effective size of mass density of a nuclei, which is about 3 orders of magnitude larger than previous bonds. What the FQXI? They didn't like their own results, so changed the rules in prediction. Let's unpack this. Mass density of nuclei refers to the degree or distance of superposition or smearing out of mass separated from itself. The more the smearing, the lower the mass density. A smear term distance is used in calculating the gravitational self-energy of the superposition. In the initial calculation, which predicted radiation, the germanium atom nucleus was considered separate from itself. In orchestrated objective reduction, this same type of superposition separation distance was calculated for the protein tubulin, a subunit of microtubules, in 3 different ways. 1, partial protein separation, complete separation of atomic nuclei, and 3, complete separation of protons and neutrons. The dominant effect and highest energy was from a completely separated carbon atom nucleus seemingly beside itself, with further separation and radiation diminish and time t lengthens. Orchestrated objective reduction, calculating for tubulin, which was then used to determine the time in terms of coherence and cognition times. Orch OR suggests these frequencies interfere to give slower cognitive response times in tens to hundreds of milliseconds. Initially, the Gran Sasso authors utilized the same side-by-side separation for larger germanium nucleus, predicting sufficient energy for measurable de-assay radiation, but when no radiation was found, the authors asserted the distance must be too small and proceeded to calculate an additional smear factor large enough so that the predicted radiation would be undetectable. This radiation 0 value smeared their hypothetical 1,000 to 10,000 fold to 10 to the negative 10th meter in angstrom, where no detectable radiation would be expected. With this accomplished is unclear, and smearing the nucleus would transition through side-by-side separation, likely to cause objective reduction and prevent further smearing. In the Crossroad article, the authors then weaponized RO against orchestrated objective reduction, creating their own de-asso variant of orchestrated OR. They smeared our 2.5 times 10 to the negative 15th meter carbon nuclear separation, an additional 4 orders of magnitude to their angstrom length, reducing the energy and prolonging time t. They then test their de-assay variant of Orch OR and find conscious response times at minimum of t equals 12 days, not very useful in survival and adaptation. The Gran Sasso authors deceptively and repeatedly conclude that Orch OR based on de-assay theory is definitely ruled out. Reply: de-asso theory includes de-assay objective reduction, which doesn't entail consciousness and seems to be refuted. An orchestrated objective reduction variant based on de-assay objective reduction is a non sequitur. Actual orchestrated objective reduction using Penrose objective reduction is most definitely not ruled out. Based on these 2 papers, the FQXI press release naively declared orchestrated objective reduction's demise in their fundamentally incoherent headline, collapsing the leading theory for the quantum origin of consciousness. Conclusion: why no radiation? De-assay objective reduction predicts detectable radiation due to diffusion of charged particles. Penrose OR predicts no detectable radiation. Penrose has proposed that OR events have retroactive effects which go back in time to get rid of the unselected curvature and prevent detectable radiation. Specifically, the retroactivity goes back in time to the earliest phase of the separation before significant particle diffusion and radiation can occur. One space-time curvature becomes classical reality, and other unselected curvatures get nipped in the bud by backward time effects as if they never existed. More generally, Penrose OR, Orch OR, and consciousness are in the domain of general relativity, space-time curvature, and quantum gravity, the fine-scale makeup of the universe. In Orch OR, consciousness is a process rooted in fundamental space-time geometry, operant in the brain via quantum processes and microtubules, and possibly detectable through techniques designed for microscopic quantum gravity waves. Okay, so there you have it. There's links to the papers of Donati and Derek Shanti in the FQXI press release. So I guess FQXI is to look. So you could see the tweet storm here with Stuart Hameroff. So there wasn't too much going on with the Science of Consciousness conference, but I guess during the conference, Stuart Hameroff sent out a few tweets. So FQXI Physics is exploring the foundation of physics and cosmology. I guess is a think tank in Georgia. So a little bit interesting there, and if people want to look at the the tweet storm, and you see Quantum Magazine, Scientific America, also connected in this. Here's Michael Levin. I shared Michael Levin in the past. So here's a new paper on basal cognition. Yeah, so there's a lot going on. So I just thought I'd share, some of the recent discoveries, going on with the Science of Consciousness conference. So I have a long paper that I want to read on. I talked about last week from Dirk Meijer that gives an overview of the various quantum related theories of mind and the connection to quantum theory. So this is pretty complicated. It's been a major topic in Week in Review for a long time. Maybe Jennifer, if she has time, will you'll be able to watch it and comment. And so I'm not sure if anyone's going to hop on. Otherwise, it probably about an hour of reading. And that's all I have for this week. So it might be a semi-shorter Week in Review unless Michael comes back or someone else wants to hop on. But I do want to get through this rather long paper that will go over all of the major schools of theories of quantum consciousness. And most models of consciousness do not include quantum processes. Like the mainstream models of consciousness, physicalist models of consciousness, do not come on to quantum effects in order to explain their consciousness, explain the phenomena of consciousness, like Grossberg, the predictive mind, active inference, IIT, integrated information theory, neural correlates of consciousness. Most of those theories claim to be able to explain consciousness without coming on to quantum effects. However, there's numerous tens of theories of consciousness, including quantum effects, that fall into a few different schools. The most advanced of them, probably the orchestrated objective reduction of quantum of Penrose and Hameroff, although there's other ones, and we mentioned David Bohm last week. So anybody tuning in, so hope Orfeo, Mark, anyone in the chat, hopefully this will be pretty interesting. So the link is in the chat here, and I'm going to go through. Maybe I'll make some comments to different parts of this. I'll share the link one more time. And this is, there's a 200-page book. So Dirk Meijer, I guess Simon Raggett, and I read a few papers from Dirk Meijer last week, who I believe is still alive in his 80s. And so this is on a UK site, and it's condensed from the 200-page book. And so I just went over the table of contents last week. And so this just has excerpts from the various sections, but It's about a 150-page book, and you could see the introduction to quantum aspect of brain function, quantum approaches to neurobiology, David Bohm, Wholeness and Implicit Order, Henry Stapp, Attention, Intention, and Quantum Coherence, Roger Penrose, Consciousness and the Geometry of the Universe, Stuart Hameroff, Objective Reduction in Brain Tubules, Hiroomi, Umezawa, and Herbert Frohlich, Quantum Brain Dynamics, Marijibu and Kunio Yasu, Quantum Field Concepts, Johnjoe McFadden, Electromagnetic Fields, Gustav Bernroider, Ion Channel Coherence, Chris King, Cosmology, Consciousness and Chaos Theory, Piero Scaruffi, Consciousness as a Feature of Matter, Danko Gurdjieff, Quantum Neuron, Andrei Krennikov, Quantum-like Brain and Other Metamorphic Quantum Mechanic Models, Hugh and Wu Persinger, Spin-Mediated Consciousness, Chris Clark, Qualian Free Will, Herms Ramage, Photon-Mediated Consciousness in Recent Models, Stuart Kaufman, Consciousness in the Poised State, Post-Bohmian Concepts of a Universal Quantum Field, Dirk Meijer, Cyclic Operating Mental Workspace, Amit Goswami, The Vacuum as a Universal Information Field, Simon Raggett, A Final Attempt to the Theory of Consciousness. So there's a whole book that I recommend people getting. And I didn't speak to Elliot during the week. I mean, if he pops in, he's welcome to chat. I actually got a whole bunch of books. I got like 500 books in today. So I didn't speak to Elliot all week. If he pops in and wants to talk, or if Amy, pops in and wants to talk, that's fine. Also, we could take a break reading through this. So this has quite a bit of the various models. Well, it doesn't have everything in the table of contents. So I encourage people to read the whole book of Dirk Meijer on the topic. But I'm going to read through this synopsis, which is a synopsis of all of the major quantum models of consciousness. Introduction and quantum aspects of brain function. Since the development of quantum mechanics and relativistic theories in the first part of the 20th century, attempts have been made to understand and describe the mind or mental states on the basis of quantum mechanical concepts. Quantum physics, currently seen as a further refinement of the description of nature, does not only describe elementary microphysics, but applies to classical or microphysical Newtonian phenomena as well. Hence, the human brain and its mental aspects are associated to classical brain physiology and are also part of the quantum physical universe. Most neurobiologists consider quantum mechanic mind theories irrelevant to understanding brain-mind processes. However, there is no single theory of quantum mechanical brain-mind theory. In fact, a spectrum of more or less independent models have been proposed that all have their intrinsic potentials and problems. The elements of quantum physics discussed here are summarized in Table 1 and 2. Details of the various quantum mechanical theories have been described elsewhere. And so people checked last week. Also, I read another paper describing some of this last week. Some quantum mechanical mind options assume sort of space-time multidimensionality. There are more than the 4 conventional space-time dimensions. Other options assume that one or more extra dimensions are associated with mental attribute, or the individual mind is partially an expression of the universal mind through holonomic communication with quantum fields. The latter ideas led to the holographic holonomic theories. The human brain is then conceived as an interfacing organ that not only produces mind and consciousness, but also receives information. The brain, or parts of the brain, are conceived as interface hologram of incoming data and already existing data. A personal universe, if properly explored, analyzed, information about the outer world can be distilled. In neurobiological terms, the existing data is equivalent to the subject's memory, whereas the analyzer is cerebroelectrophysiology. Bohm hypothesized that additional dimensions are necessary to describe quantum mechanical interference processes, thereby circumventing probabilistic theories and conscious-induced collapse of the wave function. In this theory, the universe is a giant superposition of waves representing an unbroken wholeness, of which the human brain is part. According to the individual mind, or consciousness is an inherent property of all matter and energy. and as such being part, or rather an expression, of this universal quantum field. The apparently diffuse time-space localization of mental function argues in favor of an underlying multidimensional space-time reality. Bohm and Hiley also proposed a two-arrow bidirectional time dimension in this concept of stochastic or double stochastic character of quantum is explained by an underlying quantum field, the implicate order. This concept implies entanglement, non-locality as well. Another hypothesis having the potential to couple wave information to mental processes proposes that wave information is transmitted from and into the brain by wave resonance. Though conscious observation, they collapse locally to material entities. Stapp argued that this does not represent an interference effect between superposed states, as assumed by Hameroff and Penrose, but that through environmental decoherence, superpositions become informative to the brain organism. A complementary implication of these theories is that mental processes are not necessarily embedded in entropic physical time. In line with the quantum mechanic idea is that memories are not stored as a temporal sequence, but rather atemporally. Some quantum mechanical mind theories suppose the possible involvement of specific molecules. A spectrum of ions and molecules has been suggested to operate in quantum manner. For instance, quantum mechanical theories have been based on microtubular proteins involved in synaptic transmission, including calcium ion channels and the channel proteins instrumental in the initiation and propagation of action potentials of potassium ion channels. There is also the hypothesis that the synaptic transmission represents a typical quantum probability state that becomes critical for an all or none neuronal response. Attributing nonlinear and non-computable characteristics of consciousness, Hameroff and Penrose argue against mechanisms of all or none firing of axonal potentials. They rather prefer the model of Davia, proposing that consciousness is related to waves traveling in the brain as a uniting life principle on multiple scales. According to some quantum mechanical mind theories, tunneling was proposed to facilitate membrane vesicle fusion in neural information processing at the synapse. Kaufman relates quantum processes in the biological matrix of the brain to the emergence of mental processing. This theory, mainly based on chromophores detecting photons, assumes that the coherence of some quantum configurations adhere to proteins is stabilized or maintained by recoherence. This principle may have guided evolutionary selection of proteins. Accordingly, mind and consciousness are both quantum mechanical and an expression by the classical neural mechanisms. The underlying coherent quantum state provides the potentiality for the collapsed decoherent material state, resulting in classical events such as firing neurons. They're at least to some extent acausal beyond classical determinacy. The quantum state of the brain interacts with the quantum environment. The phase information is lost and cannot be reassembled. By entanglement, the quantum coherence in a small region like the cell or the brain might have spatial long-range effects. Kaufman accepts the long-lived coherent states in biological molecules at body temperature to be potentially enabling parallel problem solving as major challenges for further investigations. The question is also which neurons or neuronal structures are in particular associated with the coherence-decoherence brain model of consciousness. The question is often put as to why quantum theory should be involved in discussions of consciousness at all, and also as to why it should be treated as something special. In thinking about quantum theory, it is important not to be bullied into viewing it as something weird and peripheral that can be ignored. Unfortunately, this allows the more superficial thinkers to dismiss all theories of quantum consciousness. This sort of practice has recently been criticized as pseudo-skepticism, a parallel form to pseudoscience. Pseudo-skepticism similarly uses denunciation in the name of science or scientific affiliation without citing any evidence or possible experimentation to establish this criticism. The feature of quantum theory that makes it special and also possibly relevant to consciousness can be summarized as follows. Quantum theory describes the fundamental level of energy and matter. In contrast to higher levels, the quantum level has aspects such as mass, charge, and spin that are given properties of the universe, not capable of further reduction or explanation. In quantum theories of consciousness, it is suggested that consciousness is such a fundamental property existing at this level. Some theories are additionally linked to the structure of spacetime, which is nowadays seen as being interconnected with the nature of the quanta. 2. The other fundamental aspects of the universe is spacetime, as described by the special and general theories of relativity. Although both relativity and quantum theory have been tested to a very high degree of accuracy, they are nevertheless incompatible with one another. The gravitational force is the main problem, since the smooth continuous curvature of space that describes gravity in general relativity is incompatible with the discreteness of particles' waves that is fundamental to quantum theory. String theory and loop quantum gravity have attempted to bridge this gap, but neither are yet regarded as giving a complete picture. 3. In traditional versions of quantum theory, the waveform of the quanta is conceived as a superposition of the many possible positions of a quantum particle. When the wave function collapses, the choice of a particular position for the particle is random. This choice of position is in effect without a cause. The property of randomness is not in itself particularly useful in theories of consciousness, but it does open a chink in the deterministic structure of the universe, which is exploited in particular by the Penrose-Hameroff model. 4. Non-locality is the remaining special feature of quantum theory. Classical physics compromises only so-called billiard ball relationships with bits of matter and energy bumping into one another. These relationships are local in that they involve immediate contact. Such relationships are also normal in quantum physics. However, quantum physics also possesses non-local relationships. This applies where two particles have been in some close relationships, such as two electrons of the same orbital. In this case, they can be correlated. For instance, the spin of two particles may always be opposite. If one spins up, the other spins down. This is not a problem while the particles are in a waveform, as both will be in superposition of up and down. However, if the wave function of one particle collapses, that particle chooses one or the other superposition. When that happens, the other particle will choose the opposite position. In experiment, this is shown to happen when the two particles are out of range of a signal traveling at the speed of light. No matter energy or conventional information is transferred, and the experiment is not regarded as a violation of relativity, but as a demonstration that quantum properties can correlate instantaneously over any distance. The failure of modern consciousness studies. The studies of consciousness was taboo in academic circles through much of the 20th century, at least in part due to the long reign of behavioralism. Even the study of emotion being largely proscribed, with brains conceived as being reasoning machines and nothing else. This started to lift in the late 1980s, and at first this seemed to be a marvelous opportunity for the advances made in other areas of science to be applied to the neglected area of consciousness. What followed, however, can be seen as overall negative in establishing orthodoxies which appear to have negligible chances of success in explaining consciousness, while discouraging explanations that relate to new areas of physics and neuroscience. The traditional explanation for consciousness or the soul in more traditional language is known as dualism. This posits a separate spirit stuff and physical stuff, with the spirit stuff capable of acting on the physical stuff, and when the soul commands the body. The core argument against dualism was for the spirit stuff to act on the physical stuff, it would need to have some physically relevant quality and would therefore not be pure spirit stuff. Vice versa looks to apply for the physical stuff. The failure of dualism is one of the few points of agreement between mainstream consciousness studies and those that identify consciousness with fundamental of the universe. Functionalism was, at least in the 1990s, the dominant explanation for consciousness, driven by the success of computers as problem-solving and memory storage machines. The main proposal is that any system or machine that possesses information in the same way as the brain will be conscious regardless of what it is made of. The biological matter and structure of the human brain was deemed irrelevant. In reality, and despite its popularity, this appears as a pseudo-theory kicking the problem of consciousness further down the road. It does not explain how consciousness arises in the brain, and nor does it explain how consciousness might at some point arise in silicon or other matter. It seems, however, that functionalism has had a malign effect in making mainstream conscious studies. Practitioners think it's unnecessary to take any notice of modern develops in neuroscience or biology. Identity theory may have been the next most popular theory after functionalism in the 1990s. This declared that consciousness was identical to the brain or identical to its processing. However, it made little attempt to explain why it was identical to the brain, but not to any other physical structures in the universe, nor did it attempt to define what it meant by the brain, despite the fact that our understanding of physical processes of the brain was changing dramatically. It was further mind by the discovery that much neural processing, such as the dorsal stream governing spontaneous movement, could be brought to completion outside of consciousness, which was seen to be more closely related to longer-term evaluations and planning. Epiphenomenalism was and remains another popular idea. The theory proposes that consciousness is a byproduct of neural processes that has, however, no function. Despite its popularity, this concept is beset by at least three major problems. It conflicts with evolutionary theory, and that it's hard to see why evolution should select for something that has no function, particularly as neural processing is exceptionally energy hungry. The theory also conflicts head-on with physics, in which there is no acausality with every object or process having influences elsewhere. Finally, there's the problem that even granting the idea of a functionless byproduct, there is still no physical evidence for what produces such a thing in the brain. Like functionalism, it appears to be a pseudo-theory. In the present century, there seems to have been a tacit recognition that functionalism and identity theory would have difficulty in becoming the consensus of a wider public. This appears to have given rise to two more theories that avoid treating consciousness as a fundamental. Consciousness resulting from embodiment has been possibly the most fashionable of these ideas. Initially, embodiment ideas did represent a genuine step forward in both consciousness studies and psychology as a move away from the brain as a computer in a vat. It now accepted that mental events could influence the body and that visceral events could feed back on the brain. It also accepted that emotion is a relevant aspect of mental life. However, there was an overreach in suggesting that the body somehow drove consciousness that the brain could not produce. This seemed to assume some kind of undefined special property in the body that was not present in the brain. More specifically, ignore the fact apart from the sense of touch, signals entered the brain directly from the environment and were consciously processed by the higher sensory and frontal cortex before being signaled to the viscera. This attempt to classify consciousness as a form of information or information processing has also become fashionable in this century. Interestingly, there are innumerable examples of non-conscious information, especially when we look at modern technology, with no apparent specification as how the conscious information would differ from non-conscious information. At a more philosophical level, there is a core difference between information and reality, in that information embraces only what we happen to know, while it can also be defined as an attempt to describe nature's behavior and macroscopic makeup that comprises reality. Thus, the hunter-gatherer in ancient Africa, glancing up at the sun, is only aware of its glare, heat, and position in the sky. A fuller understanding of its reality has to wait for modern science. A popular but poorly based concept is to call consciousness an emergent property. This idea of consciousness as an emergent property of classically described matter is superficially plausible, and as such can sometimes look like the best shot of modern consciousness studies. Emergence is a familiar process in physics. Thus, liquidity is an emergent property of water. The individual component hydrogen and oxygen atoms do not have the property of liquidity. However, when they are bound together in a sufficiently large number of water molecules, the property of liquidity emerges. The problem for this explanation of consciousness is that when emergent properties such as liquidity arise in nature, the emergence can be traced to the component particles and forces, such as the electromagnetic interaction between the water molecules. The macroscopic liquidity is an effect of the microscopic electric charge and the resulting charge relationships. The problem for consciousness as an emergent property, it is no arrangement of such particles and forces has been identified that could produce consciousness. Many continue to furiously assert that it is possible, but the claim being made here is in fact the same as dualism, where two things that have no common property are required to act on one another. Anybody who thinks it is possible in physics could simplify their search for consciousness by accepting the idea of dualistic spirits. In the last 2 decades, consciousness studies has gone off in a different direction from physics or neuroscience. Much of consciousness studies is dominated by philosophers and psychologists who have only a scant interest in what has been happening in brain science, let alone physics. In many cases, they see as their duty to prop up a 19th century Newtonian worldview, while dealing in abstractions that take limited account of neuroscience or physics. Neuroscientists have meanwhile been pressured into treating consciousness as not part of their remit, deferring to philosophers when it was necessary to discuss consciousness, even when the philosophy was contradicted by the neuroscientists' own discoveries. More fundamental approaches have fallen victim to black propaganda against them. It seems likely that the mainstream consciousness studies, if it survives at all, will reach the end of the 21st century without having achieved consensus on a theory that has explanatory value. The descent into the quantum world. Suppose one were to ask for a scientific description of your hand. Biology could describe it in terms of skin, bone, muscle, nerves, blood, and this might seem a completely satisfactory description. However, if you were just a bit more curious, you might want to know what the muscle and blood were made of. Here you would descend to a chemical explanation in terms of molecules and proteins, water, and the reactions and relations between these. If you're still not satisfied with these, you would have to descend into the quantum world. At this level, the solidity and continuity of matter dissolves. The molecules of protein are made up of atoms, but the atoms themselves are mainly vacuum. Most of the masses of the atoms lie in small nucleus, comprised of protons and neutrons, which are themselves made up of smaller particles known as quark. The rest of the mass of the atom resides in a cloud of electrons orbiting around the nucleus. So here's some of the central elements of quantum physics: uncertainty of position of particles, wave-particle duality, as demonstrated by the double-slit experiment, as well as entanglement, non-locality of particles at great distances, the phenomena of coherence, decoherence, and superposition of waves. The fundamental particles are bound together by the four forces of nature, which are gravity, electromagnetism, and strong and weak nuclear forces. The strong nuclear force binds together the particles in the nucleus of the atom and acts only over the very short range of the nucleus itself. Gravity is the long-range force that mediates the mutual attraction of all objects possessing mass. The electromagnetic force is perhaps the most apparent in everyday life. We are familiar with the form of light, microwaves, and X-rays. It holds together the atom through the attraction of the opposite electric charges of the electron and proton. It also governs the interaction between molecules. Van der Waals forces, a weak form of electromagnetic force, is vital to the conformation of protein and thus the process of life itself. In contrast to nuclear forces, gravity and electromagnetism are conceived as extending over infinite distance, but with their strength diminishing according to the inverse square law. That is, if you double your distance from the object, the gravitational attraction will be 4 times as weak. The quantum can be divided into two main classes: the fermions, which possess mass, and the bosons, which convey energy or the forces of nature. The most fundamental fermions are the quarks, making up the nucleus, and the circulating electrons, where gluons and photons are the most prominent. Bosons, the gravitrons, which may intermediate the gravitational force, remain hypothetical. The quantum wave. The quantum particles of quanta are unlike any particles or objects that have encountered in the large-scale world. When isolated from their environments, they are conceived as having the property of waves, but when they are brought into contact with the environment, there is a process of decoherence in which the wave function is described as collapsing into a particle. The wave form of the quanta is different from the waves in matter in the large-scale world, such as the familiar waves in the sea. These involve energy passing through matter. By contrast, the quantum wave can be viewed as a wave of the probability for finding a particle in a specific position. The probability wave also applies to states of the quanta, such as momentum. While the quanta remains in its wave form, it is viewed as a superposition of all the possible positions that the particle could occupy. At the peak of the wave, where the amplitude is greatest, there's the highest probability of finding a particle. When the wave eventually collapses, however, the choice of position for each individual particle is completely random, representing an effect without a cause. This comprises the first serious conceptual problem in quantum theory. The two-slit experiment in quantum mechanics. The physicist Richard Feynman said that the classic experiment contained all the problems of quantum theory. In the early 19th century, an experiment by Thomas Young showed that when a light source shone through two slits in a screen and then onto a further screen, then a pattern of light and dark bands appeared on the further screen, indicating that light was in some places intensified, in other places reduced or eliminated. Where two waves of ordinary matter, for instance, waves in water, come into contact, an interference pattern forms by which the waves are either doubled in size or canceled out. This appearance of the phenomenon in Young's experiment demonstrated that light was a wave, contrary to most scientific opinion prior to the experiment. Later, the experiment was refined. It could now be performed with one or two slits open. If there was only one slit open, the photons of light quanta or any other quanta used in the experiment behave like particles. They pass through the one open slit interacted with the screen beyond and left an accumulation of marks on that screen, signifying a shower of particles rather than a wave. But once the second slit was opened, the traditional interference pattern indicating interaction between two waves reappeared on the screen. The ability to generate the behavior of either particles or waves simply according to how the experiment was set up showed that the quanta had a perplexing wave-particle duality. The wave-particle duality was shocking enough, but there was worse to come. Technology advanced to the point where photons could be emitted one at a time and thereby impacted the screen at one at a time. What is remarkable is that with two slits open, but the photons impacting one at a time, the pattern in the screen formed itself into the light and dark bonds of an interference pattern. Somehow the photons knew to arrange themselves into a pattern indicative of the interaction of waves. The question arose as to how the photons emitted later in time knew how to arrange themselves relative to the earlier photons in such a way that there was a pattern of light and dark bands indicative of interacting waves. The obvious solution was to place photon counters at the two slits in order to monitor what photons were up to. However, as soon as the photon is registered by the counter, it collapses from being into a wave into a particle, and the wave-related interference pattern is lost from further screen. The most plausible way to look at it may be to say that the wave of the photon passes through both slits, or possibly that it tries out both routes, and after doing this, the divided wave interferes with itself. The EPR experiment and the Copenhagen interpretation. Einstein disliked the inherent randomness involved in the collapse of the wave function. This was despite the fact that his revival of the idea of light in the form of discrete particles or quanta had contributed to the foundation of quantum theory. He sought repeatedly to show that quantum theory was flawed, and in 1935 he seemed to have produced a masterstroke in the form of the Einstein-Podolsky-Rosen experiment, EPR. At the time, this was only a thought experiment, a mental simulation of how a real experiment might proceed, but since 1982, it has been possible to perform this as a real experiment. Quantum entanglement in a pair of distant elementary particles with regard to spin. So that's the diagram there. The challenge to quantum theory presented by the EPR experiment hinges on the concept of locality and non-locality. Locality comprises the idea of normal cause and effect under which objects or particles move or change as a result of being impacted by other objects or particles, or being directly acted on by energetic forces such as electromagnetic waves. If it is local, because the object or force producing the action or charge has to be in direct contact with the object or particle acted on. Moreover, when a force emitted by one object acts on another distant object, such as light emitted from the sun acting on the Earth, the force passes between the two objects at a speed not greater than that of light. By contrast, non-locality involves the ability of one particle to determine the behavior of another distant particle instantaneously and without any matter or energy passing between the two. Einstein termed this spooky action at a distance. With the EPR experiment, it was shown that as it stood, quantum theory violated the principle of locality, which is normally regarded as basic to scientific thinking and even to common sense. Quantum theory indicated that when two quantum had been closely related to one another, for instance, in the same electron orbital, they could be regarded as quantum entangled. In this state, certain aspects of the behavior in relation to one another became fixed. For instance, quantum particles have a property of spin, which is partly analogous to the spinning of large-scale objects. Quantum can have the property of spin up or spin down. If the entangled state particles could have the relationship that when one had a spin up, the other would always have a spin down. However, as quanta, while they remained in wave form, they both represented a superposition of spin up and spin down, and therefore neither of them had a defined spin. The EPR experiment proposed that two such waveform particles are moved apart. This could be a few meters along a laboratory bench or to the other side of the universe. The relevant consideration is that the two locations should be out of range of a signal traveling at the speed of light. Now, if an observation is made up on one of the particles, its wave function collapses. It acquires a defined spin, let's say spin up in this case. Now, when an observation is made on the other particle, it will always be found to have the opposite spin. This defines the normal expectation of classical physics that a random choice of spin would produce approximately 50% of the same spin, 50% different. Therefore, there's seen to be some non-local connection between the two particles, although it is not possible to describe or detect this in terms of a normal physical transfer of energy or matter. The non-locality and the randomness of the outcome of the wave function collapse constitutes the two main puzzles in quantum theory. The Copenhagen interpretation of the EPR experiment, the idea of non-locality, which appeared to deny much of what the science of the previous 300 years had been trying to establish, was as repugnant to the leaders of the quantum movement, such as Niels Bohr, as it was to Einstein as an opponent of quantum indeterminism. Some modern analysis suggested that Bohr changed his own view of the quantum world in a crucial manner after encountering the EPR challenge. Bohr's interpretation is known as the Copenhagen interpretation, and the form of this that emerged after 1935 essentially denied the objective existence of or reality of the quantum wave. Bohr said that there was no quantum world, there was no deep reality. The quantum only achieved objective reality when they were the subject of an experiment or observation. The concept of reality or objective existence is here taken to mean that something exists when it is not being observed by anyone. The Copenhagen interpretation denies that sort of reality to the waveform of the quantum. The wave was to be seen only as an abstract mathematical expression, allowing one to predict the probable position of a particle if the waveform had no real existence. EPR-type situations did not involve any physical action at a distance, and the problem could be deemed to have gone away. The aspect experiment of non-locality, the Lane aspect. The question returned to the fore in the 1980s as technology overtook the original EPR thought experiment. In 1969, John Bell's theorem had shown mathematically how EPR could be tested, and in 1982, Aspect's experiment demonstrated the physical reality of EPR. The Aspect experiment did not invalidate Copenhagen, but it transferred the whole debate from the hypothetical to the scientifically tested level. It presented physics with a stark choice. Either one could accept the Copenhagen interpretation, in which the locality of interactions was preserved, but the components of matter and energy was unreal, or one could have a world that was real, but in part governed by non-local influences, Einstein's dreaded spooky action at distance. In fact, recent decades have seen a growing challenge to the orthodoxy of Copenhagen. This leaves us without a generally agreed interpretation of quantum theory. The Copenhagen interpretation preserved us from non-locality, but the concept of the quantum as a mathematical abstraction that suddenly produced physical particles may be viewed as troubling. It seems to propose a sort of dualism compared to the relationship between spirit stuff and physical stuff. How could mental constructs such as mathematical formula become physical without having had some physical reality in the first place? Other interpretations have come more to the fore in recent decades. Decoherence has become particularly popular as a substitute for the traditional measurement always referred to in the Copenhagen version. In decoherence, the collapse of the wave function happens of its own accord as a result of the wave becoming entangled with the rest of the environment. In some recent versions, it is suggested that there is no collapse. The information in the wave simply gets lost in the larger scale environment. In some quarters, this is argued to provide a connection to the many worlds interpretation. In this, there's also no collapse, but a branching of reality into separate universe. So in the Schrödinger cat paradox, for instance, the universe splits into one universe with a live cat and one with a dead cat. Quantum gravity in the search for reality. The success of quantum theory, which describes matter and energy, and of relativity, which describes space and time, have both been marred by the incompatibility of these two theories. Relativity describes gravity as the smooth, continuous curvature of space under the influence of massive objects, while quantum theory is based on the idea of energy and matter coming in discrete, discontinuous units. Mathematically, these contrasting features lead to infinities, indicating that something is wrong. The attempt to overcome these problems has led to new theories such as string theory or loop quantum gravity. Wave-particle duality in quantum physics should be rather seen as a state in which particles and waveforms are complementary features in hidden reality. And Puzzi et al. Showed that the waveform is a physical reality. Principles of quantum physics are presently used in a large variety of technologies. The conscious observer or the detector that observes the double-slit system and provides interpretable data collapses the wave function to a single-slit pattern. String theory proposes that the fundamental particles are not point particles as has been assumed, but one-dimensional strings extending into higher dimensions beyond the normal 4 dimensions. The extra dimensions are generally deemed to have been rolled up in very small in the Big Bang, which accounts for them never having been detected. The manner in which the strings vibrate determines the nature of the particle involved. The analogy is that the strings of the violin, where the vibration of the string determines the nature of the note. While this may appear both speculative and improbable, it has the advantage of being described by mathematics that would allow quantum theory and relativity to be compatible. The two main criticisms of string theory are that it produces 10 to the 500th possible universes, and that it operates against the background of fixed space-time, a concept that relativity showed to be invalid. An alternative approach is provided by loop quantum gravity, LQG. This approach approaches the problem from the direction of relativity and concepts of space-time in contrast to string theory, which approaches from the point of view of particles in quantum theory. Loop quantum gravity proposes that space-time is quantized in discrete units. Space-time is suggested to be created out of a network or lattice or a series of loops. This theory is drawn on the earlier spin network theories developed by Roger Penrose and moves towards viewing particles and space-time as dual aspects of the same thing. Problems and opportunities in quantum theory. We have emphasized 3 problematic aspects of the theory: a causality in the randomness of the wave function collapse, a causality in the non-local influences demonstrated by the EPR type experiments, and the resulting lack of agreement as to underlying reality of the physical universe. At a quantum level, we find properties of mass, charge, and spin that are given properties of the universe lacking cause or explanation. If we ask what is the charge on the electron, what is it, not what does it do, the answer will be a resounding silence. The quanta and related spacetime appear to be the only level of the physical universe where it might be possible for science to insert consciousness as an additional fundamental property. Timescales for neural processes and consciousness. Okay, so there we had the background to okay, just make sure the sound's working. So there we had the background to quantum mechanics, and now we're going to turn towards consciousness. So that was relatively brief but conclusive overview of the background of quantum mechanics, and now we'll show how that relates to consciousness, and then the article Dirk Meijer will go over most of the major quantum theories of consciousness. Just want to make sure my sound's working and continue reading. Okay, sounds good. Okay, timescales for neural processes and consciousness. In looking at the possible physical underpinnings of neuroscience, Gurdjieff contrasts what is for conscious studies the still dominant Newtonian orthodoxy of deterministic causes and effects with quantum physics, in which there is a multitude of potential outcomes rather than a single determined outcome. Gurdjieff discusses epiphenomenalism, the theory that consciousness is a byproduct of brain processes having only an illusion of causal influence. He points out the evolutionary argument against this view to the effect that evolution would not select for something that conveyed no selective advantage. In general, he sees the idea that we have no freedom or moral responsibility as counterintuitive. Such a counterintuitive result is seen as the inevitable consequence of explanations based on deterministic classical physics. Quantum mechanics does, however, provide a non-deterministic alternative in which consciousness underlies the neural processing of making choices and thus affecting future possibilities. The author goes on to discuss the vexed questions of possibility of quantum coherence in the brain. Mainstream consciousness studies has managed to fabricate an orthodoxy to the effect of quantum coherence cannot occur in organic matter. A paper by the physicist Max Tegmark is often quoted in this respect. Tegmark asserted what was already an established position to the effect that quantum coherence in the brain would be too short-lived to have a functional role in neural processing. Tegmark's paper was aimed at refuting Hameroff's orchestrated objective reduction theory, which requires quantum coherence to be sustained for 25 milliseconds. Thus, Tegmark did not show that coherence over shorter timescales could not support consciousness because he was directing his argument at the longer timescales of Hameroff's theory. Gurdjieff here queries whether there is any evidence that consciousness has to arise over a millisecond's timescales. If consciousness could operate over a picosecond or shorter timescale, then Tegmark's calculations do not present any problem for quantum consciousness. It is pointed out that all neuroscience has been able to show to date is that consciousness does not operate on a scale slower than milliseconds. Tests show that there is a minimum time scale of about 30 milliseconds needed for a subject to distinguish between two sensory inputs as being separate. This means that consciousness cannot be slower than 30 milliseconds. However, patients with time agnosia who have subjective experience in the passage of time confirm that it's physically possible to have consecutive conscious steps that are experienced as simultaneous. From this, it is argued that the real units of consciousness could be at the picoseconds level, although such units cannot be discerned by the conscious subject. It is argued here that the upper possible bound of the timescales of consciousness need not be in the actual scale. As an analogy, Gurdjieff takes the example of the operation of a personal computer. The computer screen is on a millisecond timescale, with the screen refreshing perhaps every 10 milliseconds. But this is not indicative of the performance of the processor, which may operate on a picosecond timescale. All that the refresh rate of the monitor can tell us is the process does not operate on a slower than 10 milliseconds timescale. In the brain, the millisecond timescale applies to the brain's communication with sensory organs and muscles, but this may not say much about its internal processing. The author goes on to argue that if consciousness arises in the quantum level, some of the conventional arguments of mainstream consciousness theory fail. He contrasts classical and quantum information. Classical information can be copied and stored, a DVD encoded with a string of zeros and ones, which can be read by an external observer, is an example of classical information. With the qubits of quantum information, it is impossible to read them because any interaction with them would alter them. All that can be done is to swap or move the information without deleting it. The inability for third parties to observe quantum information is similar to our inability to observe first-person consciousness, while in contrast, such inability is alien to the classical information system. The author argues that it's impossible to copy minds that are based on quantum states because of the non-cloning theorem, which demonstrates that its attempts to copy quantum results in the quantum being corrupted. In mainstream conscious studies, philosophers and others have sought to create wonderment by arguing that it's possible to copy minds, and this appears to be true in principle if consciousness is based on classical physics. However, consciousness arises from quantum states, this becomes impossible. The possibility of copying a mind has also been used in a somewhat convoluted argument against the existence of the self. So the table, the history of quantum physics and quantum brain theory. 1805, Young's double slit experiment. 1860, Maxwell's electromagnetism laws. 1870, Boltzmann gas laws, movement of particles. 1900, Planck quantum aspects of energy. 1905, Einstein special relativity theory. 1908, Minkowski four-dimensional spacetime. 1915, Einstein's general relativity theory. 1913, Bohr structure of the atom. 1919, Kalamazoo fifth-dimensional general relativity, electromagnetism. 1923, de Broglie wave-particle duality, hidden variables. 1924, Alfred Latka, quantum brain and mind-brain relations. 1925, Pauli, bosons and fermions and elementary particles. 1925, Schrödinger wave equation for electromagnetic particles. Also Heisenberg's uncertainty principle in quantum physics. And Uhlenbeck, Gauss-Schmidt's electron spin phenomenon. 1926, Born, statistical description of wave-particle duality. 1927, Bohr measurement and quantum mechanics of Copenhagen interpretation. Also Planck-Heisenberg zero-point energy field. 28, Dirk quantum electrodynamics quantum field theory. And Arthur Eddington quantum mechanics determinism of brain function. 1930, Fritz London, Edmund Bayer, consciousness creates reality. 32, John von Neumann, relation between quantum mechanics and consciousness. 1934, Haldane, quantum wave character and life. Also Niels Bohr, the mind and quantum mechanics are connected. 1940, Wheeler-Feynman, absorber theory. 42, Casimir, experimental proof of zero-point energy. 48, Gabor holography. 51, Bohm hidden variables, pilot waves, and implicate orders. 55, pardon me, Pauli-Young synchronicity. 57, Everett, pardon me. 1957, Everett many world hypothesis. 61, Wigner conscious collapse quantum state. Ooh, got a hiccup there, sorry. 67, Wheeler quantum flavored dynamics of elementary particles. 66, Eccles-Beck quantum effects of synaptic transmission. 67, Riccardi Umezawa quantum neurophysics. 1970, Prigogine non-equilibrium dynamics, unilateral time. 1971, Pribom, the holographic brain. 72, Clauser, experimental proof of quantum entanglement. 74, Schwartz, superstring theory. And Walker, quantum tunneling and brain processing. 76, Theory of the self and mind brain concepts. 78, Stuart, Takahashi, Umezawa, quantum brain dynamics. 1982. Yeah, thanks, Mark. Sorry about that. 1982, Aspect, experimental quantum correlated particles. 1980, Kramer, transactional interpretation of quantum physics. 86, Burrow-Tipler, anthropic cosmological principle. And Frohlich, Bose-Einstein condensates in biology. And Penrose, quantum gravity-induced reduction of wave function. 1988. Stephen Hawking's multiverse concept. 89. Ian Marshall, Zohar, consciousness and Bose-Einstein condensates. In Puthoff, particle inertia and zero-point energy. Michael Lockwood, brain, mind, and quantum. 1991, Zurek, decoherence and quantum function by environment. 92, Schlemp, the quantum principle in MRI and brain scanning. Smolin, loop quantum gravity in black holes, multiverse. 1992, also Hameroff, Penrose, the microtubule consciousness theory. Python, mind-matter interaction and active information. 93, Goswami, the self-aware universe. And Herbert, the elemental mind. 94, Henry Stapp, calcium ions, neural coherence and free will. 95, Edward Witten, M-string theory. And Jibu Yasu, order, water, and superradiance. Gordon Globus, quantum cognitio. 1996, Price, backward causation. And Chalmers, the hard problem of consciousness, panpsychism. 1998, Scott Hagen, microtubuli, biophoton emission. 2000, Wheeler, the participatory universe. 2001, Wolf, mind into matter and the soul. 2000, Vitiello, dissipative quantum model of the brain. 2002, Hupeng Wu, spin-mediated consciousness. 2003, Zellinger, information and quantum teleportation. 2004, Laszlo, the informed universe, non-local illustrative field. 2003, Primus, tense time and matter and mind. 2005, Yasu and Umezawa, bioplasm and quantum brain dynamics. 2006, Scaruffi, consciousness and elementary particles. 2006, Deutsch, fabric of reality, quantum computing in the multiverse. 2012, King, cosmology of consciousness. 2013, Hameroff and Penrose, modified Orch OR brain model. Because in this argument, copying the mind would create a paradox of two identical selves. However, if copying minds is impossible, the paradox will not arise. So, okay, so enjoy your burger. Vegetarian. Yeah, so I read through that whole timeline. Just you'll get a long feel for the connected history of quantum mechanics, physics, and consciousness studies, and where we're holding now. So I'm only 1/3 through this paper. So, people enjoying this, they're in for the long haul. the link to this paper is in the chat. I'll put it there again if people want to read along. So I'm still in the introduction still, that we're going to get to all the various actual theories. Quantum mechanical approaches in neurobiology, the state of the art. The following section, taken from Meijer and Korf, discusses the idea that physical quantum concepts do physically apply to the mind. The mental domain is considered an aspect of the wave information. A special position takes the feature of superposition. Quantum particles can be present in multiple spatial locations or states and be described by one or more pure state wave functions simultaneously, of which a single state can finally be selected. Penrose suggested that the underlying space-time geometry is in fact bifurcates during the superposition process, and wave collapse occurs in a non-computable manner. It was suggested that conditions found in the microtubule could allow coherent quantum particles to form a unity that can be described by a single wave function. These concepts are considered the hard quantum theories, as opposed to the soft or formal theories of the previous section. Quantum mechanical adherents referred often to Wolfgang Pauli, the eminent quantum scientist who suggested that the mental and material domain are governed by a common ordering principle and should be understood as complementary aspects of the same reality. The hard mental quantum mechanical theories apply either to specific brain structure molecules or to quantum fields and dimensions, or both. Vanini and De Corpo, Hu and Wu, and Tarlaki listed and attempted to categorize the various published quantum brain models without a detailed treatment of the individual models. Vanini and De Corpo distinguish models based on consciousness creating reality, models based on probability aspects of quantum mechanics, and models based on already established quantum mechanics order principles. Hu and Wu differentiate in models based on quantum mechanic elements of entanglement and coherence, and models on the relationship of quantum mechanics with consciousness that can include materialistic models. Consciousness emerges from the material brain, dualistic mind-matter models, and panpsychist models. The first two papers emphasize the potential testability of the various models. More detailed reviews can be found with the latter. Tuzninsky, who was in this latest spat with Hameroff, the latter as an introductory chapter of the instructive book Emerging Physics of Consciousness, while an excellent and critical overview of the field is provided by Ottmanspracher. And I looked at the Ottmanspracher paper last week. A number of more or less specific scientific journals are currently or were devoted to the subject. Neuroquantology, Quantum Biosystems, Mind and Matter, and Antimatters, Stanford Encyclopedia of Philosophy also provides an excellent reference. Additional publications on the topic can be found in J. Consciousness Exploration and Research, New Dualism, Dualism Review, Journey of Cosmology, Scientific Exploration, Biosystems, Cognitive Neurodynamics, Science and Consciousness Review, Journal of Mathematical Psychology, Chaos, Solitons and Fractals, Open Systems and Information Dynamics, International Journal of Quantum Chemistry, the Noetic Journal, Neuroscience and Behavioral Reviews, Experimental Neurology, Journal of Mind and Behavior, Physics of Life Reviews, Syntropy Journal, Biological Cybernetics. The Journal of Consciousness Studies is an excellent source for various models of consciousness. Before we delve into the physical aspects of the quantum brain, a number of common misunderstandings on quantum mechanical modeling should be dealt with. There's no single theory of quantum mechanical aspects of brain function. In fact, a spectrum of more or less independent models have been proposed. They all have their intrinsic potential and problems. In spite of the introduction already in the first part of the 20th century and the spectacular successes of the theory ever since, some still see quantum physics as a sort of esoteric part of science. However, it rather represents a revolutionary refinement in classical physics, for example, taking into account that the theory was required in order to build an adequate atomic model, and more recently to explain experimentally demonstrated teleportation of particles, as well as principles of downward causation and time symmetry. It also the basis for laser, semi, and superconductance and microchip technology, as well as MRI brain scanning. It should also be kept in mind that classical physics can be fully derived from quantum physics, not the other way around. Quantum physics is, by some, rejected since so many interpretations of the theory are at stake. Copenhagen's many worlds, implicate order, interaction theory, micro-macro scale definition, environmental decoherence, relational quantum mechanics, etc. Yet a number of common elements, such as true particle wave aspects, instead of only a probability function, superposition, entanglement, non-locality, and coherence-decoherence phenomenon, are experimentally established and remain very usable in practice, although the related semantics should be carefully defined. It is often stated that quantum wave information coherence cannot be maintained long enough for the brain due to interaction with the macro environment and brain components. Yet, on this point, major difference in decoherence time calculations exist, as based on various models and their intrinsic assumptions. The central point here is the subcomponents could be present at the molecular or submolecular level that by their special arrangements are quantum noise protected or coherence stabilized. Examples are internal parts of the channel proteins, the stabilization by clustered arrangements of cytoplasmic water clusters. The latter authors propose a hierarchical model encompassing nerve cell depolarizations, gel solution transitions of resulting in disconnection of microtubuli, shape, volume, pulsation of dendrites, including the reorganization of synaptic contracts, and finally, transition stabilizing a new state. Though coherence and microscopic entanglements, lifetime of wave information can be much longer than the classical phase as a consequence of coherence, decoherence, dynamic equilibria, allowing non-local remote interaction in a large number of entangled neurons. Such oscillations could even be primary to excitation depolarization triggered by normal sensory stimuli and are supposed to interact with zero-point vacuum dipole vibrations. It should be realized that decoherence does not per definition imply destruction of information, since firstly is not compatible with the quantum principle of non-cloning and non-deletion. Secondary, a cyclic process of decoherence and recoherence processes cannot be excluded. While thirdly, even if such decoherence does occur, it may result in mixture of possibilities that may be accommodated by the collection of perceivable worlds in the brain. It has been proposed that the decoherent state can be converted back to a coherent state by the input of adequate phase and amplitude information. The resulting coherent states can last long enough in warm biological systems in order to, for example, enable coherent search processes for antenna-mediated transport of photon energy in photosynthesis. The author postulates that similar poised realm or microdomains on the edge of chaos could also be instrumental in human brain as sites where dynamic interplay of decoherence and recoherence take place. It is often assumed that quantum mechanics is only valid for a description of nature on the microscale. Yet convincing evidence was more recently presented that quantum physics can be applied to macromolecules, and to the surprise of many, even can occur in warm and wet biological systems and brains of birds in relation to magnetic sensing and navigation. Lloyd concluded, quantum coherence plays a strong role in photosynthetic energy transport and may also play a role in the avian compass and sense of smell. In retrospect, it should also come no surprise that quantum coherence enters into biology. Biological processes are based on chemistry, and chemistry is based on quantum mechanics. If an organism can attain an advantage in reproduction, however slight, by putting quantum coherence to use, then over time natural selection has a chance to engineer the necessary biochemical mechanisms to exploit that coherence. Different types of quantum processes that operate at the same time scale can interact strongly, either to assist or to impede one another. In photosynthetic energy transfer, the convergence of quantum timescales gives rise to the more efficient and robust transport. Evolved biological systems exhibit the quantum Goldilocks effect. Natural selection pushes together timescales to allow quantum processes to help each other out. The spectrum of atoms, molecules has been suggested to operate in quantum manner. Calcium and potassium ions, water, enzymes, membrane receptors, and channel proteins, membrane lipids, neurotransmitter molecules, in addition to macromolecule structures such as DNA, RNA, gap junctions, presynaptic vesicles, microtubules, and microfilaments. Since our integral universe can be described by the current laws of quantum mechanics and relativity, it does not seem warranted to place the human brain outside nature. Some see even cosmic architecture mirrored in our complex brain. The discussion around higher brain function is frequently obscured by modalities of promissory materialism. At present, we do not understand consciousness, but within 20 years, the problem will be resolved. Not only is such an extrapolation scientifically unwarranted, but certainly cannot be falsified. Even more damaging is the assumption that one will find the solution by further using current technology instead of postulating new models and innovative experimental approaches. Some quantum mechanical models are based on the interaction of brain components with experimentally detected quantum fields. The central aspect of realistic quantum field theory holds that the essence of material reality is a set of fields. These fields obey the principles of special relativity in quantum theory, and the intensity of a field at a point gives the probability for finding its associated quantum and the fundamental particles that are observed by experimentalists. These fields may holographically project into each other, implying interactions, interpenetrations of their associated quantum waves. Vitiello proposes a virtual shadow brain working in a time-reverse mode that stabilizes coherence of neural memory structures. It could be worthwhile to project neo-Darwinism and its biological evolutionary theories against the canvas of potential quantum mechanic mechanisms, in the sense that parallel quantum superpositions and backward causation mechanisms can provide explanations and or alternatives for evolutionary jumps in so-called emergent phenomena. Recently, models were proposed for the transfer of information in biological evolution on the basis of quantum formalisms. On the basis of quantum mechanic concepts, one should be prepared to envision uncommon and even utterly strange manifestations of quantum entanglement. Certain transpersonal human experiences should not be seen as potentially be explained by quantum mechanics, but rather require by the concept that our world is part of a quantum universe. Quantum mechanics and the higher brain functions. Here we discuss current quantum mechanical theories as possible theories bridging the classical neuronal and mental concepts. Quantum mechanical theories does indeed apply to the same brain physiological phenomena, but introduce also typical features such as particle-wave duality, entanglement, and non-locality, as well as wave interference and superposition. In addition, processes such as quantum coherence and resonance of wave interactions are at stake. So here we can see quantum brain models. So we have Amoroso, Bequai and Martin, Beck and Eccles, Bernroider, Bohm, Culbertson, DeBase, Flanagan, Frohlich, Goswami, Gurdjieff, Herbert, Hu and Wu, Jarviletto, Josephson, Kavarinam, King, Lockwood, Marshall, Mender, Hameroff and Penrose, Panera, Pitkinen, Prebram, Ramage, Satinover, Sarfati, Stapp, Talbot, Umezawa and Riccardi, Vanimi and De Corpo, Vitello, Walker, Wolf, and Yasu. So a lot of people there's a lot of theories out there. So just make sure my sound's working. Continue. So a lot of okay, so a lot of material here. It is not our purpose to assess the various quantum mechanic theories in detail. Rather, we intend to discuss some of their major implications regarding the concept of a quantum brain. The key positions of proteins in the quantum-mediated initiation and execution of mental activities was already emphasized. Several quantum mechanical theories are based on specific properties of proteins, as for instance, microtubular proteins, proteins involved in facilitating synaptic transitions, as well as specific channel proteins instrumental in the initiation and propagation of action potentials. Quantum mechanical theories also extend to the mind to different spaces and time dimensions, and some consider the individual mind as an expression of a universal mind through a holonomic communication with quantum fields. In the latter approach, the human brain is conceived as an interfacing organ that not only produces mind and conscious, but also receives information necessarily for full deployment of these mental phenomenon. The central question here is whether neuronal cells are the sole units for information processing in the brain rather than subcellular organelles or molecules. Some aspects of quantum brain models: synaptic transmission by vesicles, exocytosis of neurotransmitter molecules, calcium channel proteins in the neuronal membrane facilitates fusion of synaptic vesicles in the presynaptic terminal. The fusion of sufficient vesicles leads to a transmitter release and depolarization of the postsynaptic membrane. This fusion process bears a quantum probability character. Major debate about these theories concerns the possibility of coherent quantum states in the warm and wet internal milieu of the brain. The defenders of the quantum brain models have argued that in vivo molecular configurations exist that enable the modulation of quantum states through efficient protection and shielding of the wave interaction compartments in the cell. The particular local collapse of the brain of the wave function in this manner produces new information as originally proposed by Eccles. This is realized by membrane protein induces fluxes in calcium or potassium that then increases the probability of fusion of neurotransmitter-filled vesicles and synapses, leading to the firing of a particular neuron or even groups of neurons. The central hypothesis here is that synaptic transitions represent a typical quantum probability state in which the total number of vesicles available for the exocytosis is critical for an all or none response of neuronal firing. Coherent neuronal perturbations, and especially their entangled states, are supposed to provide a non-local binding of sensory and cognitive brain centers. It may also enable perception of qualia and the unitary sense of a conscious self. As the mesoscopic scale of the brain activity, where the binding process is expected to occur, is in the vicinity of the quantum domain, the binding principle is likely to be a quantum non-local effect, probably the only known physical mechanism able of performing such a task. One possibility is the information of a quantum photonic field. Another possibility is the formation of coherent states on the level of transmembrane ion fluxes, such as calcium. Hameroff and Penrose argue against mechanisms of all or none firing of exonal potentials as suggested by Beck and Eccles, since such binary states do not include nonlinear and non-computable characteristics of consciousness. They rather prefer the model of Davia, proposed that consciousness is related to traveling waves in the brain as a uniting life principle on multiple scales. The latter is based on energy dissipation, enzyme catalyst, protein folding, and maintains energy balance, is an excitable system such as the brain conditions that are also compatible with the isoenergetic brain model treated in Meijer and Korf. Nonlinear in brain processes is modeled using the well-known Schrödinger equation, adjusted with a nonlinear term, as proposed earlier by Walker, by which robustness of a classical approach is combined with the more flexible elements of quantum theory. The originators of this hypothesis, Penrose and Hameroff, have discussed that microtubules in principle can maintain quantum states lasting at least 10 to the negative 6 seconds, long enough to be instrumental in the transfer of quantum wave information. Such lasting quantum states are possible because the shielding of hydrophobic pockets in the particular proteins, as well as the formation of coherent clusters of these molecules that thereby share a quantum wave function, so-called Bose-Einstein condensates. There is indirect evidence that microtubules may be relevant for neurocognition, increased synthesis in relation to postnatal development with regard to synaptogenesis and visual learning, and as counterpart aging deficits in memory, as well as interaction with general anesthetics. Yet such correlative studies should not only be further substantiated with experiments that show quantum states in isolated tubules, as reported by Bandapade, but rather, and most importantly, directly demonstrate tubular involvement in higher brain functions in situ. More recently, in 2013, Bandapade's group demonstrated that in microtubules, the energy level of up to 40,000 individual tubulin proteins and the energy of the microtubular are the same. The water core of the individual tubulin proteins are suggested to control the properties of the microtubule by means of a delocalized electromagnetic oscillation. The properties of the microtubule might be taken to suggest that the system can support a macroscopic quantum state. The author said that prior to the 2013 paper, the properties of the tubulin and microtubulars were not extensively studied using the up-to-date technologies mentioned here. Theories that apply to metals, insulators, and semiconductors are not relevant to microtubules. In conclusion, tubular and synthetic channels per protein exhibit conformational transitions with a 10 to the negative 9th seconds that may last for 10 to the negative 6 seconds or even longer. These perturbations may last long enough to finally be detected as miniature neuronal potentials. The particular mechanism also implied manifestation of non-local quantum effects due to distance coherence, a phenomenon that was even recorded in laser-stimulated neuronal cell cultures in which classical physical explanations were excluded. The coherence of such quantum states among brain proteins has been suggested to lead to material changes in brain physiology through orchestrated collapse of the quantum coherent clusters of tubulin proteins triggered by the quantum gravity expressed on the spin Planck scale level, on the basis of a recent theory of the nature of gravity, postulating that gravity is not a force but rather an entropic compensation for the movement of mass information. It was speculated that consciousness may arise from gravity-mediated reaction of the entropic displacement of information as occurs in high density in the human brain. Anyhow, there should be a mechanism to integrate signal processing within a single neuron with other even distant neurons, and consequently non-local effects due to quantum entanglement should play a role also in this case. These quantum processes may explain phenomena such as qualia, meaning, sensation of unity, intentionality, as well as conflict solving, reliability, and the sense of correspondence with the outer world and the sense of self. The latter is related to the feeling of causal power that could result from a quantum classical interference in which classical synaptic processes create a quantum coherent state that enables quantum computation that exert a back influence to the original synaptic process. The existence of non-locality in brain function being a basic property of the universe strongly argues for the underlying deep reality out of space-time as originally proposed by Bohm. In the form of implicate order, Bohm claimed that these mechanisms also play a role in different forms of transpersonal and extrasensory perception by wave resonance with the universal quantum field. The main issue of the present essay is the wave information provides a potential coupling to mental processes. For instance, wave information could be transmitted from and into the brain by wave resonance and may locally collapse the matter entities through conscious observation, including sufficient individual attention and intention. Stapp argued recently that this does not represent an interference effect between superposed states, as assumed by Hameroff and Penrose, but that through environmental decoherence, superpositions will be converted to multiple mixtures of information. Since our brain contains a large collection of perceivable worlds, it is able by supercausal free choice and subsequent common random choice to make a fit with one or more of the above-mentioned mixed information modalities. The particular waves then spread out in rapid sequent repetitions, the so-called Zeno effect, may sufficiently maintain coherence in parts of the brain. Of note, Stapp does not see free will as based on quantum probability aspects. He states in the original Copenhagen formulation, this extra process is initiated by what is called a free choice on part of the experimenter. The phrase free choice emphasizes the fact that while a definite particular choice is needed, the choice is not determined by any known law or rule. The purely physical aspect of the theory have, therefore, a significant causal gap, which opens the door to a possible causal input from the mentality side of reality. Quantum information may exert physical effects via the bottom-up flow of information starting at spin networks that can be passed on as waveforms of an elementary particle's atoms to be ultimately expressed at the level of neuronal molecules. Meijer and Korf consider the latter flow of information more feasible than being directly transferred through vibratory interference at the molecular level. According to the integral quantum model, perturbations at the various spatial temporal domains allow both space-time symmetric forward and backward causation, and therefore top-down influence in quantum fields. The basic question is, how are quantum waves or quantum fields finally perceived by the human brain, and how are they influenced or even induced phenomenon as self-consciousness? Organisms do indeed visually perceive photons that exhibit wave-particle duality. Humans even sense less than 10 photons, whereas insects may even detect a single photon. Sensitive detection is possible with dedicated cellular structures, as for instance the mammalian retina that amplifies the energy of a single photon by a cascade of processes based on changes of protein conformations and cellular potential energy, leading to the electrochemical stimulation of neurons projecting to the brain. Recently, photosensitive proteins have been coupled to ion channel proteins with biotechnical techniques so that the neural activity can be modified or inhibited in vivo by light introduced via optic microfibers. These experimental approaches demonstrate that quantum effects may directly affect neural function, but it remains to be shown more definitely that this also does occur directly inside the human brain, as it was demonstrated in the brain of birds. Quantum information mechanisms were recently used to model human consciousness, as well as the unconscious in relation to conscious perception, in which various modalities of non-locality were discussed. Of note, entanglement and non-locality may not only apply to spatial separation, but also a temporal one. It was proposed by Martin that the archetypes can be stored as quantum systems and that consciousness may be controlled by quantum entanglement from outside spacetime. Although this cannot be easily envisioned, Niculescu made clear that the relationship between different levels of reality have to be interpreted in the framework of Gödel's incompleteness theorem, and that it may be intrinsically impossible to construct a complete theory for describing the unity of all levels of reality. Interestingly, a recently five-dimensional spacetime brain model was proposed in order to adequately position consciousness and universal consciousness in the cosmos, an item that was discussed earlier, suggesting that consciousness may be in a brain rather than in the brain. Ottmansbacher explained that mind-matter correlations may require new science, in the sense the use of emergence and reductionism schemes may not be adequate and should be replaced by possibly symmetry breaking within a domain in which matter and mind are unseparated. He cites D'Espinat postulating an independent ultimate reality that is neither mental nor material. Another issue is whether more or less random quantum events can be orchestrated in such a way that the information becomes meaningful for the brain. Thus, the major challenge is to directly demonstrate that proteins such as microtubules, potassium channels, or synaptic vessels, and associated protein becomes informative to the organism. It has been put forward that a combination of quantum mechanisms and nonlinear chaos theory have to be considered in the amplification of subtle external information necessary for immediate action. Further information may be realized by time reversal sensing of such an event on the basis of the attractor state. According to the supercausal model of consciousness of Chris King, the constant interaction between information coming from the past and information coming from the future leads to the quantum entities that are always confronted with bifurcations between past and future causes. This involves fractal structures and chaotic dynamics that enable free choices to be performed. Consequently, consciousness should be a property of all living structures in which each biological process is forced to choose between information coming from the past and information coming from the future. Such models attribute consciousness to principles of relativity, quantum physics, and fractal geometry on the basis of established physical applications of these theories would, in principle, allow experimental testing to falsify them. It is of interest that top-down recurrent connections in higher order in the associative cortex was shown to be indispensable conscious perception. In more general terms, processing and amplification of quantum wave information in the brain may underlie the presumed higher brain or mental functions. If one assumes that such detection mechanisms does indeed operate in the brain, then the next question is whether the information is to be processed is exclusively associated with a quantum wave or quantum states, or alternatively with the specific proteins that carry them. Apart from discussing the inherent mechanisms such as forward and backward causation, superposition, and entanglement in the mental space, we shortly treat the idea that the individual mind may at least partially be an expression of a universal consciousness, as opposed to the concept of mind as merely an attribute of matter. Okay, so thanks for tuning in. And now we've completed the introduction to quantum mechanics, the overview of how quantum mechanics affects consciousness, with an overview of the theories and the main ideas contained within the various theories. And now we will look at individual various quantum mechanical theories of consciousness. David Bohm, Wholeness and the Implicate Order. David Bohm and Louis de Broglie. David Bohm took the view that quantum theory and relativity contradicted one another, and that this contradiction implied that there existed a more fundamental level than the physical universe. He claimed that both quantum theory and relativity pointed towards this deeper theory. This more fundamental level was supposed to represent an undivided wholeness and an implicate order, for which arose the explicate order of the universe as we actually experience. The explicate order is seen as a particular case of the implicate order. The implicate order concept of David Bohm, in which particles in the more complex forms in our classical world are steered by so-called pilot waves that operate from a four-dimensional hidden domain in a mode of active information. The implicate order applies both to matter and consciousness, and it can therefore explain the relationship between these two apparently different things. Mind and matter are here seen as related projections into our explicate order from the underlying reality of the implicate order. Bohm claims that when we look at the extension of matter and separation of its parts in space, we can see nothing in these concepts that helps us with understanding consciousness. Bohm compares the problem to Descartes' discussion of the difference between mind and matter. Descartes, to some extent, relies on God to resolve the gap. Bohm says that since Descartes' time, the idea of introducing God into the equation has been let drop, but he argues that the result convention, modern thinking, has in no way left to it for bridging the gap between matter and consciousness. In Bohm's scheme, there's an unbroken wholeness at the fundamental level of the universe in which consciousness is not separated from matter. Bohm's view of consciousness is closely connected to Karl Pribram's 1991 holographic conception of the brain. Pribram sees sight and the other senses as lenses without which the universe would appear as a hologram. Pribram thinks that information is recorded all over the brain and that this information is enfolded into a whole, also in the manner of a hologram, although it's suggested that the physical function involved is more complicated than a hologram. In Pribram's scheme, it is suggested that the different memories are connected by association and manipulated by logical thought. If the brain is also attending to sensory data, all of these facets are proposed to fuse together in an overall experience or on unanalyzable whole. This is suggested to be closer to the essence of consciousness than the mere excitation of neurons in trying to arrive at the description of consciousness. Bohm discusses the experience of listening to music. He thinks that the sense of movement and change that constitutes the experience of music relies on notes both from the immediate past and the present being held in the brain at the same time. Bohm does not view the notes from the immediate past as memories, but as active transformation of what came earlier. He proposes that given moment can cover an extended duration as opposed to the more conventional now concept of something instantaneous. The moment is proposed to have extensions in time and space, but the amount of this extension is not precisely defined. One moment gives rise to the next, with content that was implicate in the immediate past becoming more explicate in the present. The sense of movement in the music is a result of the intermingling of transformations. Bohm likens these transformations to the emergence of consciousness from the implicate order. He thinks that in listening to music, people are directly perceiving the implicate order. The order is thought to be active and flow into emotional physical responses. Bohm also discusses the problem of time, the concept of now, and the difficulty of distinguishing now from the immediate past, which no longer exists. In classical physics, the problem is overcome via the calculus with its concept of the limit, which is effectively a zero change in time or space. This is successful for calculating the movement of material objects in classical physics, which comprises the explicate order. However, it is not applicable to quantum theory, in which movement is not seen as continuous. In the implicate order, intermingled elements are present together, and processes are the outcome of what is unfolded in the implicate order. In this structure, there is a flow between experience and logical thought that is considered by Bohm to hold out the possibility of a bridge between matter and consciousness. Bohm also advocates the idea of overall necessity driving short-term brain processes. This is proposed that an ensemble of elements enfolded in the brain will constitute the next development of thought, and that these elements are bound by an overall necessity that brings them together and also determines the next moment in consciousness. Bohm relates movement to the implicate order. For movement, we can also read change or flow or the coherence of our perceptions of a piece of music over a short period of time. Evidence for this claim to derive from studies of infants from Piaget who have to learn about space and time, which are seen as part of the explicate order, but appear to have hardwired understanding of the movement that is implicate. Bohm's view is that the movement and flow of the implicate order are hardwired into human brains in the same way that Chomsky asserts that grammar is hardwired into the human brain, but that by way of contrast, the classical space and time of the explicit order are something that has to be learned by experience. Basil Healy was a long-term associate of David Bohm and continued exponent of many of his ideas. Healy argues that Bohmian notion of active information introduced in relation to quantum phenomenon can also be applied to classical signaling. This is suggested to have relevance to concept of meaning as opposed to mere information. Highly queries whether the word information that is widely used in science, including neuroscience, also carries the same meaning. Bohm and Highly were interested in so-called active information that drives physical processes and leaves no choice as to whether they are implemented or not. This is distinct from a mere list of data instruction or a way of viewing entropy. Active information has been used in a number of papers relative to the mind-matter relationship. The colloquial understanding of information is that it is data from which meaning can be extracted by an intelligent entity. Highly regards it as a fundamental question as to whether information has objective significance devoid of the subjective involvement. Verbal communication is seen as a particular problem where meaning is translated into sound waves and then back into meaning. Highly relates this meaning to the agency of the speaker and the agency of the listener. He relates this inseparable link to Bohm's notion of the indivisibility of the quantum action, which cannot distinguish between the system under observation and the means of observation. Bohm believed that quantum potential could be extracted from Schrodinger's equation, and that this quantum potential could act as an information potential. In transmitting a signal, there is a trade-off between the duration of the pulse and the frequency. There's ambiguity in the signal that is similar to the uncertainty of quantum mechanics. The two concepts are said to employ different aspects of the same mathematical structure. Highly refers to the two-slit experiment, where the potential is claimed to cover the whole experimental arrangement. The quantum information changes is in relation to any change in the experimental arrangement, and this is related to information entering the brain and changing the arrangement of its parts. Within the brain, Bohm thought that meaning was in the process itself. Bohm proposed that there was two sides or two poles in the brain, the manifest and the relatively stable material side, and the subtle mind-like side. The manifest side in classical physics, while the subtle side is the quantum level that produces the classical level. Thus, the mind cannot be separated from matter. The ambiguity or uncertainty of quantum comes through the ambiguity attached to meaning. The quantum is seen as a pool of information shared by entangled particles. When the potential or pools vanishes, the classical world emerges. Highly also agrees that the system could operate in terms of quantum fields. The main weakness of this description seems to be the lack of details as how the quantum mechanisms would operate in the brain, and the lack of distinction between information which does not itself imply consciousness and consciousness itself. The emergence of meaning could be thought to imply consciousness, but this important point is not at all developed. So the ink drop experiment, David Bohm, that we talked about 2 weeks ago with David Douglas from the Philippines. In the 1960s, Bohm began to take a closer look at the notion of order. One day he saw a device on a television program that immediately fired his imagination. It consisted of two concentric glass cylinders, the space between them being filled with glycerin, a highly viscous fluid. If a droplet of ink is placed in the fluid and the outer cylinder is turned, the droplet is drawn out in a thread that eventually becomes so thin that it disappears from view. The ink particles are unfolded into the glycerin, but if the cylinder is then turned in the opposite direction, the thread form reappears and re-becomes a droplet. The droplet is unfolded again. Bohm realized that when the ink was diffused through the glycerin, it was not in a state of disorder, but possessed a hidden or non-manifest order. In Bohm's view, all the separate objects, entities, structures, and events in the visible or explicate world around us are relatively autonomous, stable, and temporary subtotalities derived from a deeper implicate order of unbroken wholeness. Bohm gives the analogy of flowing stream. On this system, one may see an ever-changing pattern of vortices, ripples, waves, splashes, which evidently have no independent existence as such. Rather, they subtract from the flowing movement, arising and vanishing in total process of the flow. Such transitory substance as may be possessed by these abstracted forms implies only relative independence of autonomy of behavior rather than absolutely independent existence as ultimate substances. Okay, so there you have David Bohm. Let's keep it going. Appreciate Mark Orfeo. I'll check the chat later. Too caught up in reading right now. I want to get through this very important stuff. Get an overview, quantum mechanics, the relation of quantum mechanics to consciousness, and the various theories on the market. Anthony Valentini. Valentini, 2002, consistently defends the pilot wave mechanisms of David Bohm, Bohm, he says, had an interesting trajectory. There are really three Bohms. There's the very early Bohm, who was interested in Niels Bohr's ideas about complementarity. Then there's the Bohm of the 1950s, who worked on the pilot wave theory of hidden variables. Then in the 1960s, he's changed again. He met Krishnamurti and got very interested in Indian philosophy and started trying to tag some mystical ideas onto the pilot wave theory. If you look at the Yoga Sutras of Patanjali, you can see the idea that the material objects are somehow illusions and projections from something deeper, that things emerge from this deeper level and disappear into this deeper level again. So indeed, Bohm tried to adopt an interpretation of the wave as a manifestation of a deeper level, perhaps associated with consciousness. Why does Valentini like the pilot wave theory? It preserves a realist ontology wherein particles possess determinate value of a space-time location and momentum. They continue to possess such values between various acts of observation measurement rather than acquiring them only in consequence of being measured with respect to this or the parameter. This allows for greater continuity with certain components of classical pre-quantum physics, such as the conservation laws respecting matter, energy, and angular momentum. The pilot wave hypothesis produces results in perfect accordance with those obtained in standard quantum mechanics by means of the Schrödinger-derived wave probability function, while avoiding any recourse to the mysterious idea of the wave packet collapse as somehow brought about by observer intervention or only on the instant in Schrödinger parable when the box is open for inspection and the cat thus releases from its supposed superposed dead or alive state. Pilot wave theory seeks to explain quantum effects such as photon deflection or multipath interference without proposing a massively expanded ontology of parallel worlds, shadow universes, multiple intersecting realities, etc. Pilot wave theory has three axioms. The first is de Broglie's law of motion, which specifies exactly how particles are guided by the wave. The second is Schrödinger's wave equation, telling us how the wave itself changes over time. The third is that particle has to start off with a certain probability distribution. In any given experiment, each particle is accompanied by a wave. The particle starts off somewhere inside the wave. In order to give results that can be verified with an experiment, all three axioms have to be used. In classical physics, there is an interplay between particle and field. Each generates the dynamics of the other. In the original pilot wave theory, the steering wave acts on the positions of particles, but is not acted upon by the particles. However, Holland has explored some deeper ideas related to the question in his work of a possible Hamiltonian formulation of the pilot wave and proposed a particle to wave back reaction. This implies that through the pilot wave mechanism, particles like waves carry information regarding their future states. It also means that particle trajectories may exert a back reaction on the wave function, implying symmetric interaction between implicate and explicate orders. What is so unusual about Anthony Valentini? He has in fact resurrected a theory that undoes the central tenets of quantum mechanics and gives relativity theory a support as well. The theory formulates quantum math, but at the same time allows for new possibilities beyond conventional quantum mechanics. It is the theory that he says is indeed an objective reality behind the things we observe. The quantum uncertainty is not fundamental, and that somewhere, somehow, time is universal, not relative. This implies goodbye to ghostly probabilities with their strange propensity for collapsing into real things, and hello to hidden variables that are objective. This seems related to the American physicist John Archibald Wheeler, who suspected that reality exists not because of physical particles, but rather because the act of observing the universe. Information may not be just what we learn about the world, it may be what makes the world. In other words, when humans ask questions about nature, there is an active transfer of information in the domain of quantum waves, where in principle backward causation from the future is possible. The second arrow from future to past remains hidden, unnoticed for us, because life is trapped in the momentum of time. Entanglement means that particles separated at any distance under certain conditions can have mutually determined properties and correlated. In this block universe, multiple paths or lifelines are laid out in which the individual chooses a single one. Consequently, this concept allows free choice and therefore is not deterministic. Such non-locality becomes manifest by observation or collapse of the wave aspect, as has been shown by electron spin orientation or polarized light. This might also be viewed as backward causation. According to Wheeler's and Feynman's electrodynamics, emitters coincide with retarded fields, which propagate into the future, while absorbers coincide with advanced fields, which propagate backwards in time. The time-symmetric model leads to predictions identical with those of conventional electrodynamics. For this reason, it is impossible to distinguish between time-symmetric results and conventional results. In this transactional interpretation of quantum mechanics, Kramer stated that nature, in the very subtle way, may be engaging in backwards in-time handshaking. The transaction between retarded waves coming from the past and advanced waves coming from the future gives birth to quantum entity with dual properties and wave particle. Thus, the wave property is a consequence of the interference between retarded and advanced waves, and the particle property is a consequence of the point in space where the transaction takes place. The transactional interpretation requires that waves can really travel backwards in time. This assertion seems counterintuitive, as we are accustomed to the fact that causes precede effects. It is important to underline, however, that unlike other interpretations of quantum mechanics, the transactional interpretation takes into account special relativity theory, which describes time as a dimension of space, as mentioned earlier. Of note, the completed transaction erases all advanced effects, so that now direct advanced wave signaling is possible. The future can affect the past only very indirectly by offering possibilities for transaction. King, 2003, stated the handshaking space-time relation implied by the transactional interpretation makes it possible that the apparent randomness of quantum events mask a vast interconnectivity at the subquantum level, reflecting Bohm's implicate order, although in different manner from Bohm's pilot wave theory, because transaction connects past and future in a time-symmetric way. They cannot be reduced to a predictive determinism because the initial conditions are insufficient to describe the transaction, which also includes quantum boundary conditions coming from the future absorbers. However, this future is also unformed in real terms at the early point of time emission takes place. The principle of backward causation has been experimentally demonstrated recently. Aronov's team at various collaborating groups studied whether the future may influence the past by sophisticated quantum physics technology. Aronov concluded that a particle's past does not contain enough information to fully predict its fate, but he wondered if the information is not in its past, where could it be? Clearly something else must also regulate the particle's behavior. Aronov and co-workers proposed a new framework called time-symmetric quantum mechanics. Recent series of quantum experiments in about 15 different laboratories around the world seem to actually confirm the notion that the future can influence results that happened before those measured were even made. The transactional interpretation of quantum mechanics of Kramer of retarded and advanced waves from the past, the future that produced the present, and the time-symmetric concept of prize-winning Aronov arising from post-selection measurement of the quantum state that prevents wave collapse and also shows that the future may affect the past. This shows that through the wave aspect, the wavicle intrinsically contains the aspect of the future. Yeah, so Michael, if you're there and you want to hop on, I'll take a break and we could talk a few minutes. I'll finish the rest of this afterwards. And the link is in the chat because there's a lot of information here. Generally, the protocol included three steps: a pre-selection measurement carried out on a group of particles, an intermediate measurement, and a final post-selection step in which researchers picked out a subset of those particles on which to perform a third related measurement to find evidence of backward causality, meaning information flowing from the future to the past. The effects of so-called weak measurements were studied. Weak measurements involve the same equipment and techniques as traditional ones, but do not disturb the quantum properties in play. Usual strong measurements would immediately collapse the wave function in superposition to definite state. The results of the various groups were amazing. Repeated post-selection measurements of the weak type changed to the pre-selection states, revealing an aspect of non-locality. Thus, it appears that the universe might have a density that reaches back and collaborates with the past to bring the present into view. On a cosmic scale, this idea could also help explain how life arose in the universe against tremendous odds and confirms that knowledge was inherited from a common information pool. Okay, just going to take a quick break and say Kriya Shema. So, as I said, this is an extremely long article, so I'm basically dedicating the whole week in review to this overview of quantum consciousness. Ollie, if you want to pop on, Michael, and talk about Shavuos or your Jewish studies or whatever, I'm happy to take a break because I've already been reading for close to 2 hours. And I probably have at least an hour more of reading. So, God give me strength, Hashem give me strength. I'm going to try to get through this whole article tonight. It's very important for people who watch Week in Review or, are interested in consciousness, especially, quantum mind. This is extremely important. So try to get down and understand as good as possible all of these various theories, the relationship of quantum mechanics to the quantum mind and the various theories on the market right now. Okay, sure, no problem. Henry Stapp, Attention, Intention, and Quantum Coherence. Stapp starts by asking what sort of brain action corresponds to a conscious thought. He criticizes the mainstream for assuming that Newtonian physics can be applied directly to the brain and claims that a quantum framework is needed to understand the brain. The Copenhagen interpretation of quantum theory was the first mainstream version and was pragmatic in recommending the theory of a system of rules that allowing the calculations of empirically verifiable relationships between observations. Stapp favors Heisenberg's refinement of the original Copenhagen position. Heisenberg thought that the probability distribution of quantum theory really existed in nature and that the evolution of this probability was punctuated by uncontrolled events, which are the events that actually occur in nature and which at the same time eliminate the other probabilities. The development of the computing during the second half of the 20th century demonstrated that thought-like or cognitive processes required internal representations not allowed for in the then prevailing behavioralist concept. However, this still did not account for conscious experience, and this period thinking or cognition came to be seen as something separate from consciousness. But Bohr and Heisenberg viewed quantum theory as a set of rules for making predictions about observations under experimental conditions. These predictions are incompatible with classical physics in respect to the prediction of non-locality. Heisenberg did not view the quantum as actual things, but as tendencies for certain types of events to occur. The orderly evolution of systems is deterministic, but this controls only the tendencies for things or propensities for events and not the actual things or events themselves. The things are controlled by quantum jumps that do not individually conform to any natural law, but collectively conform to statistical rules. Stapp bases his proposal for quantum consciousness on 3 observations. 1, the brain's representation of the body or body schema must be represented by some form of physical structure in the brain. 2, some brain processes, such as the behavior of calcium ions involved in synaptic transmissions, need to be treated quantum mechanically. Stapp also thinks that the sensitivity of nonlinearity of the synaptic system, the involvement of calcium ions in the large number of metastable states into which the brain could evolve, all point to quantum mechanical system. And 3, Stapp suggests that the brain could evolve into a state analogous to the deterministic evolution of the quantum state from which an actual state must be selected. Although Stapp pays a lot of attention to the synapses, his is not actually a neuron-based theory. Rather, the event could be selected from the large-scale excitation of the brain. The selection of events from a wide range of probabilities is seen as being particularly adaptive, where an organism needs to select from a range of future probabilities. Stapp wishes to establish the relationship between mind and matter, the relationship between reality and quantum theory, and also how relativity is reconciled with both experience and non-locality. The solution is suggested by a series of created events, bringing into being one of a range of possibilities created by prior events. He suggests that consciousness exercises top-level control over neural excitations in the brain. The neural excitations are regarded as a code, and each human experience is regarded as a selection from this code. He sees the physical world as a structure of tendencies in the world of the mind. He finds it unacceptable that there is an irreducible element of chance in nature as described by quantum theory, which is the most usual conclusion to be drawn from the randomness of the wave function collapse. The element of conscious choice is seen as removing chance from nature. He distinguishes between systems where an external representation and knowledge of the laws of physics can accurately predict how the system develops, and his own idea of the system that is internally determined in a way that cannot be represented outside the system. The brain is viewed as a self-propagating computer with self-sustaining neural patterns as the codes. It is necessary to integrate the code from sensory input with the code from previous experience. This creates a number of probabilities from which consciousness has to select. The conscious act is the selection of a piece of top-level code, which then exercises control over the flow of neural excitation. The unity of consciousness thought comes from a unifying force in the conscious act itself. It selects a single code from amongst the multitude on offer in the brain. Raising an arm involves a conscious act selecting the top-level code that raises the arm. This is suggested to close the traditional explanatory gap between thought and classical physics, because here the conscious thought is the selection of the code that allows the physical act. Stapp goes on to discuss the conscious process of looking at pictures. According to him, top-level codes instruct lower-level codes to produce new top-level codes and to initiate their storage in memory. The experience of noticing something is deemed to be the process of initiation into memory. There are close connections between top-level code and the memory structure. The lower-level codes have to be functioning correctly, not damaged, and to be focused on the incoming stimuli in order for it to be put into higher-level code and to be registered into memory. Stapp discusses what neural research would need to reveal if it were to support his theory. It would need to reveal the neural connections needed to support self-sustaining patterns of neural excitation. It is necessary to find the neurons provided the top-level coding, then the mechanisms for storing memory traces of this, and finally the mechanisms by which these memories are involved in the production of new top-level codes. Each conscious experience is seen as a creative act represented in the physical world by the selection of a top-level code from among the many generated by the laws of quantum theory. The conscious experiences are the initiation of process that produces changes in the body schema and the external and internal reality schema. The conscious act is functionally equivalent to changes in the physical world as represented in quantum theory. In the Heisenberg version of quantum theory, physical things are events, and quantum theory gives the propensity for particular events to occur. This is seen as providing a link between conscious processes and brain processes. In this Heisenberg version, it is the act of observation which leads to the selection of a particular propensity. Stapp attaches great importance to the idea of the formation of a record. This is seen as analogous to the Geiger counter that registers a record of a quantum event. Every conscious experience is seen as a recordable because it is evidence of some form of brain process. The latter retrievable of the experience is evidence of a record in the brain. A key process in brain dynamics is seen as persisting patterns of neural excitation producing physical changes in neurons that enable a particular pattern to be re-excited and allow re-excited pattern to connect with new stimuli. This is seen as the basis of the brain's associated memory. The top-level brain process is viewed as a process of actualizing symbols composed of earlier symbols connected to the whole by neural links. The top-level process is seen as directing information gathering, planning, and choice of particular plans, monitoring the execution of plans. This can be understood in terms of top-level direction of multiple neural processes because the top-level directive role is connection to associated memory and the multiple structure of the symbols involved. It is suggested that each top-level event corresponds to a physiological event, and this in turn connects physiological events to the quantum level. Both the top-level brain event and the physiological event act as choosers of a possibility or converters of potentialities into actualities. Each human conscious experience is seen as the feel of an event in the top level of processing in the human brain, a sequence of Heisenberg actual events actualizing a quasi-state pattern of neural activity. Activation of particular symbols creates a tendency for the activation of other related symbols. The body schema is the product of actualized events accumulated over the life of the body. The top-level symbols have compositional structure formed from other symbols. The Heisenberg events are seen as being capable of grasping a whole pattern of activity, and this is seen as accounting for the unity of consciousness. The continuity or flow of time is explained by an overlap of symbols with the preceding mental event. Stapp, drawing on studies of infants, assumes that humans have a hardwired body-world schema. Consciously directed action is seen as a projection of this body-world schema into the future with a corresponding representation of the brain. The body-world schema is seen as directing the unconscious brain, issuing commands for motor action and instructions for mental processing. Ongoing questions to nature continue to be posed by the observer. This equates to the Heisenberg choice, where the human observer has to decide what question to put to nature. In this case, it is the conscious processing of the brain that does this. Each experience leads to further updating of the system. When an action is initiated by a thought, this usually includes some monitoring of the subsequent action to check it against the intended action. So something experienced as an intention becomes an action, the attention to which is also experienced. Stapp views the deterministic unfolding matter, according to the Schrödinger equation, as running parallel to the movement from intention to attention as two poles of the same quantum event that prolong the coherent state and thereby protect against potential decoherence. He also sees the tripartite structure being the Schrödinger equation, the Heisenberg choice of question to ask, and the direct choice of answer from nature. Stapp's point is that only a conscious observer within the brain can ask the question and drive the quantum process. This also allows the experimental process to enter into the causal structure of the body-brain. Stapp feels that some additional process is needed, and the conscious observer is a perfect candidate. He sees quantum theory as informational in nature and thus linked to increments in knowledge occurring in the brain. The increment in knowledge is seen as linked to reduction in the quantum state, thus linking mind to the physical world. Mind is thus seen as entering into the physical world through the Heisenberg choice. When the quantum state is produced, a wave that extends over an indefinite amount of space is instantaneously reduced to a tiny local region. Stapp feels that this constitutes a representation of knowledge rather than a representation of matter. The wave before collapse is seen as a matter of potentiality or probabilities, which are themselves often conceived as ideas rather than reality. However, the quantum state pre-collapse evolves in line with the deterministic Schrödinger equation, giving the state some of the properties of the physical, thus and creating a sort of hybrid. Stapp does not suggest that our conscious thoughts are completely unconstrained, but he does see our thought as part of the causal structure of the mind-brain that is not dominated by the actions of the smallest components of the brain, but is also not random effect. Our thoughts are not seen as linked to external objects, but instead linked to patterns of brain activity. Stapp points out that his theory has a place for the efficacious conscious mind linked to the physical processes of the brain. He suggested the dynamic of the Schrödinger evolution, which is to produce an event that replicates the event that produced it, could somehow stand in for the later action of conscious minds. The identity theory of mind claims that each mental state is identical to the same process of the brain. However, classical physics says that the entire causal structure of a physical system is determined by the microscopic level of the physical structure, so that the larger scale effects such as consciousness cannot have any influence. A potential problem with the whole Copenhagen influence interpretation of quantum theory is its possible dualism. Mathematics can be seen as a mental process instantiated in protein, which in principle cannot directly influence the external world. Somehow the mathematical description of the quantum waves is sitting out there in space, and then as a result of the measurement becomes a physical particle. In Copenhagen, a mental concept external to the body seems to become physical with no explanation as to how the two could interact. The Copenhagen system has the additional problem of what was happening before human minds emerged to perform measurements, for which Stapp's explanation appeared rather sketchy. Consequently, a more detailed model is required to picture the inherent interaction between a more general form of consciousness as a measuring device in evolution. Roger Penrose, Consciousness and the Spacetime Geometry of the Universe. Roger Penrose is one of the very few thinkers to consider how consciousness could arise from first principles rather than merely trying to shoehorn it into 19th century physics, and his ideas appear to be a good starting point for which to try and understand consciousness as a fundamental. Penrose's approach was a counterattack to the functionalism of the late 20th century, which claimed that computers and robots could be consciousness. He approached the question of consciousness from the direction of mathematics. The centerpiece of his arguments is a discussion of Gödel's theorem, Gödel demonstrated that any formal system or any significant system of axioms, such as elementary arithmetic, cannot be both consistent and complete. There will be statements that are undecidable because, although they are seen to be true, but are not provable in terms of the axioms. Penrose's controversial claim that Gödel's theorem as such is not controversial in relationship to modern logic and mathematics, but the argument that Penrose derived from it has proved to be highly controversial. Penrose claimed the fact that human mathematicians can see the truth of a statement that is not demonstrated by the axiom means that the human mind contains some function that is not based on algorithms and therefore could not be replicated by a computer. This is because the functioning of the computers is based solely on algorithms, systems of calculations. Penrose therefore claimed that Gödel had demonstrated that human brains could do something that no computer was able to do. Arguments against Penrose's position. Some critics of Penrose have suggested that while mathematicians could go beyond the axioms, they were in fact using a knowable algorithm present in the brain. Penrose contests this, arguing that all possible algorithms are defeated by the Gödel problem. In respect to arguments as to whether computers could be programmed to deal with Gödel's propositions, Penrose accepts that a computer could be instructed as to the non-stopping property of Turing's halting problem. Here, a proposition that goes beyond the original axioms of the system is put into computation. However, the proposition is not part of the original formal system, but instead relies on the computer being fed with human insights so as to break out of the difficulty. So the apparently non-algorithmic insights are required to supplement the functioning of the computer in this instance. An unknowable algorithm. Penrose further discusses the suggestion of unknowable algorithm that enables mathematicians to perceive the truth of statements. He argues that there is no escape from the knowability of algorithms. An unknowable algorithm means an algorithm whose specification could not be achieved, but an algorithm is in principle knowable because it depends on natural numbers, which are knowable. Furthermore, it is possible to specify natural numbers that are larger than any number needed to specify the algorithm action of an organism, such as a human or human brain. Mathematical robots. Penrose says that with a mathematical robot, it would not be practical to encode all the possible insights of mathematicians. The robot would have to learn certain truths by studying the environment, which in turn is assumed to be based on algorithms. But to be a creative mathematician, the robot will need a concept of unassailable truth. This is a concept that some things are obviously true. This involves the mathematical robot having to perceive that a formal system H implies the truth of its Gödel proposition, and at the same time perceiving that the Gödel proposition cannot be proved by the formal system H. It would perceive the truth of the proposition follows from the soundness of the formal system, but the fact that the proposition cannot be proved by the axioms also derives from the formal system. This would involve a contradiction for the robot, since it would have to believe something outside the formal system that encapsulated its beliefs. Among experts in this area who do not entirely reject Penrose's argument, Pfefferman has criticized Penrose's detailed argument, but is much closer to his position than that of the mainstream consciousness studies. Pfefferman makes common cause with Penrose in opposing the computational model of mind and considering that human thought, in particular mathematical thought, is not achieved by the mechanical application of the algorithms, but rather by trial and error, insight, and inspiration in a process that machines will never share with humans. Pfefferman finds numerous flaws in Penrose's work, but at the end he informs his readers that Penrose's case would not be altered by putting right the logical flaws that Pfefferman had spent so much time discovering. Pfefferman's own position is that the computational mind argument is misleading in terms of the weight that it places on the equivalence between Turing machines and formal systems. The model of mathematical thought in terms of formal systems is considered to be closer to the nature of human thought, in particular mathematical thought, than the functioning of Turing machines. The Turing machine model would assume that a given problem human reason would plug away, implying the same algorithm indefinitely in hope of finding an answer. Pfefferman says that it is ridiculous to think that mathematics is performed in this way. Trial and error reasoning, insight, and inspiration based on prior experience but not on general rules are seen as the basis of mathematical success. A more mechanical approach is only appropriate after initial proof has been arrived at. Then this approach can be used for mechanical checking of something initially arrived at by trial and error and insight. He views mathematical thought as being non-mechanical. He says that he agrees with Penrose that understanding is essential to mathematical thought, and that is just this area of mathematical thought that machines cannot share with us. Quantizing space-time twister of Penrose. The motivation And one of the initial aims of the twistor theory is to provide an adequate formalism of the union of quantum theory and general relativity. Twistors are essentially complex objects like wave functions in quantum mechanics, as well as endowed with holomorphic and algebraic structure sufficient to encode space-time points. In this sense, twistor space can be considered more primitive than the space-time itself, and indeed provide a background against which space-time could be meaningfully quantized. The twistor theory was more recently applied to the string theory of Edward Witten. The twistor theory, as proposed by Penrose, defined a basic structure for space-time geometry. As it also attempted by string theories, twistor theory was later applied by Witten in the universal string M theory to diminish the total number of required extra dimensions. Penrose's own take on the wave function collapse suggested that as a real event, he sees superposition as a separation in the underlying space-time geometry. Each quanta is embedded in a bit of space, and as the superposition grows further away, a blister of separation appears in space-time. This can be viewed as the same thing as the beginning of the multiple world view, but instead of going on to generate separate universes, if the separation between superpositions grows to more than the Planck length, the wave collapses and chooses one of the superposed alternatives. Twistor theory in the context of space-time has been pioneered by Roger Penrose and others since the 1960s and is based on the association of a complex twistor space, CP3, to the space of light rays in space-time. The name derives from the Robinson congruence, which is the neutral realization of a non-null twistor. Penrose thereby attempted to encode space-time points, affording a quantized space-time. Some appealing aspects of the theory are twistor space becomes the basic space so that light rays are fundamental objects from which space-time is derived. Discrete quantities such as spin are represented in the discrete values obtained by contour integration. Its evidence, elegance, and simplicity. The normal quantum wave collapse is seen as an entirely random choice of the state of quantum particles from amongst the various superposition of states. However, these collapses involve interaction with the environment. Penrose suggests that a quanta which does not interact with the environment will undergo objective reduction when the separation between superposition begins to exceed the Planck length. He also suggests that while a normal collapse is total random, objective reduction is not totally random but involves a non-computable process. This is suggested because Penrose thinks that the brain manifests a non-computational aspect and that the wave function collapse is the only place in the universe where such a thing can exist. Penrose also proposes that objective reduction-based quantum computation occurs in the brain. Penrose searched for a non-algorithmic feature. Penrose went on to ask what it was in the human brain that was not based on algorithms. The physical law is described by mathematics, so it's not that easy to come up with a process that is not governed by algorithms. The only plausible candidate that Penrose could find was the collapse of the quantum wave function, where the choice of the position of a particle is random and therefore not the product of an algorithm. However, he considered that the very randomness of the wave collapse disqualifies it as a useful basis for the mathematical judgment or understanding in which he was initially interested. The wave function in respect of consciousness. It is Penrose's attitude that the reality of quantum wave function collapse that is the important area. In particular, he disagrees with the traditional Copenhagen interpretation, which says the theory is just an abstract calculation procedure and that the quantum only achieves objective reality when a measurement has been made. Thus, in the Copenhagen approach, reality somehow arises from the unreal or from abstraction, giving a dualist quality to the theory. The discussion of quantum theory repeatedly comes back to the theme that Penrose regards the quantum world and the uncollapsed wave function as having objective existence. In Penrose's view, the objective reality of the quantum world allows it to play a role in consciousness. Penrose emphasizes that the evolution of the wave function portrayed by the Schrödinger equation is both deterministic and linear. The aspects of quantum theory is not random. Randomness only emerges when the wave function collapses and gives the choice of a particular function or other properties for a particle. Penrose discusses the various takes made on wave function collapse by physicists. Some would like everything to depend on the Schrödinger equation, but Penrose rejects this idea because it is impossible to see how the mechanisms of this equation could produce the transformation from the superposition of alternatives as found in the quantum wave to the random choice of a single alternative. He also discusses the suggestion that the probability of a quantum wave that emerges into macroscopic existence arises from uncertainties in the initial conditions, and that the system is analogous to chaos in macroscopic particles. This does not satisfy Penrose, who points out that chaos is based on nonlinear developments, whereas the Schrodinger equation is linear. Important distinctions between Penrose and Wigner. Penrose also disagrees with Eugene Wigner's suggestion that it is consciousness that collapses the wave function. On the basis that consciousness is only manifest in special corners of spacetime, Penrose himself advances the exact opposite proposal, that the collapse of a special objective type of wave function produces consciousness. It is important to stress this difference between Penrose and Wigner position, as some commentators mix up Wigner's ideas with Penrose is propositions on quantum consciousness and then advance a refutation of Wigner, wrongly believing it to be a refutation of Penrose. Penrose is also dismissive of the many worlds version of quantum theory, which would have an endless splitting into different universes with, for instance, Schrodinger's cat alive in one universe and dead in the other. Penrose objects to the lack of economy and the multitude of problems that might arise from attempting such a solution, and in addition, argues that the theory does not explain why the splitting has to take place and why it is not possible to be conscious of superpositions. Objective production, consciousness, spacetime, the second law, and gravity. Penrose instead argues for some new physics, and in particular, in addition, form of wave function collapse if the superposition described by the quantum wave extended into the macroscopic world. We would in fact see superpositions of large-scale objects, and this does not happen. It is argued that something that is part of objective reality must take place to produce this reality that we actually see. This requirement for new physics is often criticized as unjustified. However, these criticisms tend to ignore the fact that while quantum theory provides many accurate predictions, there has never been satisfactory agreement about its interpretation, nor has its conflict with relativity been resolved. Perturbation of space-time curvature by quantum state reduction. Neuronal tabulus of the potential site of quantum-mediated effects in the brain. Each tubulin is shown to have 9 rings representing 32 actual phenol or indole rings per tubulin, which couple oscillating London force dipoles orientation among rings traversing quantum channels, aligning with rings in adjacent tubulins in helical pathways through microtubule lattices. On the right, the superposition of the alternative tubulin in helical pathway dipole states. Penrose sees consciousness not only as related to the quantum level, but also to spacetime. He discusses the spacetime curvature described in general relativity. He looks at the effect of singularities relative to two spacetime curvature tensors, Weil and Ricci. Weil represents the tidal effect of gravity, by which the part of the body nearest to the gravitational source fastest, creating a tidal distortion in the body. Ricci represents the inward pull on the sphere surrounding the gravitational force, and a black hole singularity, the tidal distortion of Weil would predominate over Ricci, and Weil goes to infinity at the singularity. However, in the early universe expanding from the Big Bang, the inward tidal distortion is absent, so Weil equals 0. Well, if is the inward pressure of Ricci that predominates. So the early universes seem to have had low entropy with Weil close to 0. Weil is related to gravitational distortions, and Weil close to 0 indicates a lack of gravitational clumping, just as Weil at infinity indicates the gravitational collapse onto a black hole. Weil close to 0 and low gravitational clumping therefore indicate low entropy at the beginning of the universe. The fact that Weil is constrained to 0 is seen by Penrose as a function of quantum gravity. The whole theory is referred to as the Weil curvature hypothesis. The question that Penrose now asks is why the initial spacetime singularities have this structure. He thinks that quantum theory has to help with the problem of the infinity of singularities. This would be a quantum theory of structure in spacetime, or in other words, a theory of quantum gravity. Penrose regards the problems of quantum theory in respect to a disjunction between the Schrodinger equations, deterministic evolution, and the randomness in which wave function collapse as fundamental. He thinks in terms of spacetime asymmetrical quantum gravity because the universe is time asymmetric from low to high entropy. He argues that conventional process of collapsing the wave function is time asymmetric. He describes an experiment where light is emitted from a source and strikes a half-silvered mirror with resulting 50% probability that the light reaches a detector and 50% that it hits a darkened wall. This experiment cannot be time reversed because if the original emitter now detects the incoming photon, there is now a 50% probability that it was emitted by the wall, but instead 100% probability that it was emitted by the other detecting emitting device. Penrose relates the loss of information that occurs in black holes to the quantum mechanical effects of the black hole radiation described by Stephen Hawking. This relates to the wild curvature that had been seen to apply to black holes in quantum wave collapse, as wild curvature is related to the second law of thermodynamics. This is taken to show that the quantum wave reduction is related to the second law of gravity. The second law anti-gravity proposes that in certain circumstances there could be an alternative form of the wave function collapse. He called this objective reduction. He suggests that the result of the evolution of the Schrödinger wave, the superposition of the quantum grow further apart, according to Penrose's interpretation of general relativity. Each superposition of the quantum conceived to have its own space-time geometry. The separation of the superpositions, each with its own space-time geometry, constitutes a form of blister in space-time. However, once the blister of separation grows to more than the Planck's length of 10 to the negative 35th meters, the separation begins to be affected by gravitational force. The superposition becomes unstable, and it soon collapses under the pressure of its gravitational self-energy. As it does so, it chooses one of the possible space-time geometries for the particle. This form of wave function collapse is proposed to exist in addition to the more conventional form of collapse. Hey, Dave Douglas, thanks for tuning in. I'm reading this long article. It's in the description. So I've been reading for like 3 hours now, and I'm going to continue reading. But if you want to read along, Dave, great article covering all the various forms of quantum consciousness theories. Evidence for non-computational spacetime. In support of this, he points out that when the physicists Dirac and Hartle studied the quantum gravity, they ran up against a problem in deciding whether two spacetimes were the same. The problem was solvable in 2 dimensions, but intractable in 4 dimensions that accord with the 4-dimensional spacetime, in which the superposition of quantum particles needs to be modeled. It has been shown that there is no algorithm for solving this problem in 4 dimensions. Earlier, the mathematician Markov has shown that there was no algorithm for such a problem, and that if such an algorithm did exist, it could solve the Turing halting, for which it had already been shown that there was no algorithm. The possible non-computable nature of the structure of 4-dimensional spacetime is deemed to open up the possibility that wave function collapse could give access to the non-computable feature of fundamental spacetime. A long-term experiment is underway to test Penrose's hypothesis of objective reduction. The experiment is currently being run by Baumeister at University of California, Santa Barbara. Involves mirrors and only 10 micrometers across and weighing only a few trillionths of a kilo in the measurement of their deflection of a photon. The experiment is expected to take 10 years to complete. This means that theories of consciousness based on objective reduction are likely to remain speculative for at least the length of that time. However, the ability to run an experiment that could look to falsify objective reduction at least qualifies it as a scientific theory. Significance for consciousness. The significance of this for the study of consciousness is that in contrast to the conventional idea of wave function collapse, this form of collapse is suggested to be non-random and instead driven by non-computable function of the most fundamental level of spacetime. Penrose argues that in contrast to the conventional wave function form of collapse, there are indications that in this case, there is a decision process that is neither random nor computationally algorithmically based, but is more akin to the understanding by which Penrose claims that the human brain goes beyond what can be achieved by a computer. The road from physics to mental phenomenon has already been frequented notoriously by Pauline Jung, and under the influence of Pauli by Heisenberg, the interaction is not limited to 3 decades-long Jung-Pauli epistolary, and the reciprocal influence have been profound. The founding role of Pauli's work in quantum physics does not need to be recalled, and the effects of quantum vision in the development of Jung's vision of the human mind have been well explored. The title of the essay by Jung and the co-authored Synchronicity as a Principle of Causal Connections could not indicate more clearly the influence of Pauli's quantism on Jung's perception of reality and the interplay of the 2 great minds before them. The self-referentially of the Euclidean approach to human consciousness has been narrated by Lewis Carroll in his thought on the looking glass. Philosophically orchestrated objective reduction perhaps aligns most closely with Alfred Norfed White, who viewed mental activity as a process of occasions, spatial temporal quanta, each endowed usually on a very low level with mentalistic characteristics which were dull, monotonous, and repetitious. They seem analogous in the orchestrated objective reduction context to proto-conscious, non-orchestrated OR events. Whitehead viewed high-level mentality consciousness as being extrapolated from temporal chains of such occasions. In his view, highly organized societies of occasions permit primitive mentality to become intense, coherent, and fully consciousness. This seems analogous to Orch OR conscious events. Shimony, Stapp, and Hameroff recognized that Whitehead's approach was potentially compatible with modern physics, specifically quantum theory, with quantum state reductions, actual events appearing to represent occasions, namely Whitehead's high-level mentality, composed of temporal chains or intense, coherent, and fully conscious occasions, these being tantamount to sequences of Orch OR events. These might possibly coincide with gamma synchrony, but with our current beat frequency ideas of gamma synchrony might more likely be a beat effect than directly related to OR reduction time. As Orch OR events are indeed quantum state reductions, Orch OR and Whitehead's process philosophy appear to be quite closely compatible. Whitehead's low-level dull occasions of experience would seem to correspond with our non-orchestrated proto-consciousness OR events. According to the scheme, OR processes would be taking place all the time, everywhere, and normally involving the random environment, would be providing the effective randomness that is characteristic of quantum measurement. Quantum superpositions will continually be reaching the threshold for OR in non-biological settings as well as in biological ones, and OR would usually take place in the purely random environment, such as in a quantum system under measurement. Nonetheless, in the Orch OR scheme, these events are taken to have a rudimentary subjective experience, which is undifferentiated and lacking in cognition, perhaps providing a constitutive ingredients of what philosophers call qualia. We term such unorchestrated, ubiquitous OR events lacking information and cognitions as proto-consciousness. Quantizing spacetime, Whitehead, actual occasions. Quantizing spacetime of Whitehead by postulating units of experience and actual occasions that have mental and physical pole and carry elements of goal, satisfaction, and beauty. They are built up from previous occasions, from societies and occasions. In this regard, Orch OR has some points in common with the viewpoint, which incorporates spiritualist, idealist, and panpsychist elements, these being argued to be essential precursors of consciousness that are intrinsic to the universe. It should be stressed, however, that Orch OR is strongly supportive of the scientific attitude and incorporates the viewpoint picture of neuroelectrochemical activity, accepting that non-quantum neural network membrane level functions might provide an adequate explanation of much of the brain's unconscious activity. Orch OR and microtubules inside neuronal dendrites of the soma adds a deeper level for conscious processes. Stuart Hameroff, Quantum Coherence in Brain Tubules. Hameroff and Penrose classify all the mainstream approaches to consciousness as classical functionalism. Functionalism takes no account of what the brain is made of or anything finer grained than the level of neuron-to-neuron connections. It believes that these connections could be copied in another material such as silicon, and that the resulting construct would be consciousness. However, Hameroff argues that although axonal spikes and synaptic connections clearly play a key role in information processing in the brain, they may not be the main currency of consciousness. Hameroff argues that quantum processes and microtubules within the dendrites and gap junctions between dendrites are the main currency of consciousness. The main case against quantum processing in the brain has always been that any quantum coherence in the brain would decohere faster than the time taken for any useful biological process. Hameroff accepts that this is in principle a valid argument. However, Hameroff claims that the microtubules may be screened from their environment by a gelatinous non-liquid ordered state that arises in the neuronal interior. A further objection to quantum processing is that even if it arose in one neuron, it would be difficult for it to communicate across the brain. This is countered by the suggestion that there could be quantum tunneling at gap junctions between neurons. In recent years, gap junctions have been discovered to be more widespread in the brain than was previously thought. They are also correlated with the 40 Hz gamma synchrony. This oscillation was one time promoted by Crick and Koch as the most promising correlate of consciousness. However, the time fell from favor with mainstream neuroscience when it was discovered that gamma synchrony correlated with dendritic activity rather than axonal spiking. In general, Hameroff argues that the emerging evidence of neurobiology has moved in favor of the Orch OR model over the last decade, notwithstanding the continued unpopularity of the theory. Hameroff summarizes his proposal in the early part of the chapter. He thinks that consciousness arises in the dendrites of the neurons that are connected by gap junctions to form hyperneurons, and that these are related to the gamma synchrony. Axonal spikes and synapses are seen as making points and inputs to and receiving outputs from the microtubular process as part of the interactive system. Hameroff touches on the famous Libet experiments that demonstrated a 500 millisecond time lag between a stimulus and a perception of its entering consciousness, although the subject is not aware of the time lag as a result of the so-called backward referral in time. The mainstream has tended to favor an interpretation resembling the Dennett multiple drafts concept, which would involve an after-the-effect reconstruction of what had happened. Hameroff, however, thinks that the backward referral in time should be taken seriously. This was also the view of Roger Penrose, who suggested the backward referral might be indicative of quantum activity, the principle of backward causation. Hameroff points out that changes in the dendrites can lead to increased synaptic activity. This is the basic ideas about learning, memory, and neural correlates of consciousness. The changes in dendrites involve the number of the arrangements of receptors and the arrangements of dendritic spines and the dendrite-to-dendrite connections. Axon potentials or spikes have been assumed to be the main basis of consciousness, but Hameroff suggests that there could be other candidates. Electrodes implanted in the brain detect mainly the activity of dendritic gap junctions plus inhibitory chemical synapses. Thus, the detected synchrony derives from the dendrites rather than axonal spikes. The main function of dendrites is seen to be handling of input signals into the neuron, which may eventually result in an axon spike. However, this is not the whole story, since many cortical neurons have dendrites but no axons. Hence, dendrites interact with other dendrites, and there can be extensive dendritic activity with no spikes. The evidence suggests that there are complex logic functions in the dendrites, and these may oscillate over a wider area while remaining below the axon spiking threshold. Many postsynaptic receptors send signals into the dendrite cytoskeleton. Gamma synchronies in the 30 to 70 hertz range have aroused interest in possible correlates of consciousness. Gray and Singer, 89, found coherent gamma oscillations in the brain that were dependent on visual stimulation. It was suggested that synchrony could solve the binding problem, which is the problem of how different inputs in the brain are bound together into a single conscious experience. It was suggested that the synchrony reflected the activity of a relevant assembly of neurons. Vrela noted that the synchrony operated whenever the process of spatially separated parts of the brain were brought together in consciousness. Gamma synchrony had been demonstrated across cortical areas, hemispheres, and the sensory motor modalities. The synchrony is involved in a range of brain activities, including perception of sound, REM, deep sleep, attention, working memory, face recognition, and somatic perception. Also, gamma decreases during general anesthesia and returns on waking from it. Hameroff regards gamma synchrony as the best overall correlate of consciousness. He further addresses the question of how gamma synchrony is mediated. There's coherence over large areas of the brain, sometimes including multiple cortical areas in both hemispheres of the brain, with zero or near zero phase lag. If the synchrony was based on axon synapse systems with a considerable lag would be expected. In fact, the lack of coherence between the synchrony of the axonal spike activity has led to a reduction in the amount of mainstream attention paid to the gamma synchrony. Hameroff points to a gap junction as the alternative to synapses for connections between neurons. Neurons that are connected by gap junctions depolarize synchronously. Gap junctions play a more important role in the adult brain than was previously supposed. Numerous studies show that gap junctions mediate the gamma synchrony. A neuron may have the gap junction connections, but not all of them are necessarily open at the same time. The opening and closing of the gap of the junctions may be regulated by the microtubules. Hameroff suggests that cells connected by gap junctions may in fact constitute a cell assembly with the added advantage of synchronous excitation. Cortical inhibitory neurons are heavily studied with gap junctions, possibly connecting each cell to 20 to 50 others. The axons of these neurons tend to form inhibitory GABA chemical synapses of the dendrites and other interneurons. Orchestrated quantum state reduction in spacetime geometry. Schematic representation of a brain microtubule built up from tubulin proteins that can undergo rapid fluctuations in three-dimensional configurations, enabling the sensing and transmission of quantum information. Hameroff moves on to discuss the role of the cytoskeleton, which is seen to determine the structure, growth, and function of neuron. Actin is the main constituent of dendritic spines and is present throughout the neuronal interior. Actin can depolymerize into a dense meshwork, and when this happens, the interior of the cell converted from an aqueous solution into a gelatinous state. Furthermore, when this happens, the whole of the cytoskeleton forms a negatively charged matrix around which water molecules are bound into an ordered state. It is noted that the neurotransmitter glutamate binding to NMDA and AMPA receptors cause gel states in actin spines. The cytoskeleton of the dendrites is distinct both from that found in cells outside the brain and from the cytoskeleton found in axons and neurons. The microtubules in dendrites are shorter than those in axons and have mixed as opposed to uniform polarity. This appears a suboptimal arrangement for a normal structural point of view, and is suggested that the conjunction of microtubule-associated proteins, this arrangement may be optimal for information processing rather than supportive structural function. These microtubule microtubule-associated proteins arrangements are connected to synaptic receptors on the dendrite membrane by a variety of calcium and sodium influxes, actins, and other inputs. Alterations in the microtubule and associated proteins networks in the dendrite correlates with the arrangement of dendrite synaptic receptors. Studies demonstrate that the cytoskeleton is also involved in signal transmission. It is suggested that the microtubule lattice is well designed to represent and process information. Tubulin was supposed to switch between the two conformations. It is suggested that tubulin conformation states could interact with the neighboring tubulin by means of dipole interactions. The dipole-dipole coupled conformation of each tubulin could be determined by the 6 surrounding tubulins. Hameroff describes protein conformation as a delicate balance between countervailing forces. Proteins are chains of amino acids that fold into 3-dimensional conformations. Folding is driven by van der Waals forces between hydrophobic amino acid groups. These groups can form hydrophobic pockets in some proteins. These pockets are critical to the folding and regulation of proteins. Amino acid side groups in these packets interact by van der Waals forces. Nonpolar atoms and molecules can have instantaneous dipoles. An integrated fire brain neuron and portions of such neurons are shown schematically with internal microtubules and dendrites and cell body soma. Involved in integration, microtubules are interrupted and of mixed polarity, interconnected by microtubule-associated proteins in recursive networks. Dendritic somatic integration with contributions from microtubule processes can trigger axonal firings to the next synapse. Microtubules and axons are unipolar and continuous. Gap junctions synchronize dendritic membranes and may enable entanglement and collective integration among microtubules in adjacent neurons. In Orch OR, microtubule quantum computations occur during dendritic somatic integration, and the selective results regulate axonal firings which control behavior. Hameroff discusses the process of anesthesia, which erases consciousness but leaves many non-conscious functions intact. Anesthetic gas molecules are soluble in lipid-like hydrophobic environments. Such areas are present in the brain, in the lipid region of cell membranes, and the hydrophobic pockets with protein. It is suggested that anesthetic gas molecules interact with amino acid groups via London forces, altering the normal action of London forces on the conformation of proteins. Hameroff discusses quantum information processing, quantum superpositions, where the quantum waves represent multiple possibilities for the state of a particle, are known to persist until quantum are either measured or naturally interact with the rest of the environment. Hameroff takes this view that the original mainstream interpretation, Copenhagen interpretation, puts not only consciousness, but the concept of reality outside physics. Alternative interpretations include the many world view, where there is no collapse but the superposition continues in multiple worlds, and David Bohm's idea in which the quantum are guided by active information. It is important to stress that quantum computing as such is not expected to generate consciousness. In quantum computers, with many researchers are now trying to develop quantum collapse, will occur as a result of measurement or interaction with the environment. It is only in the event of objective reduction that non-computable in consciousness could be brought into play. Hameroff goes on to look at some of the detail of the theory that he and Penrose developed as to how consciousness could be based in microtubules in the brain. It is suggested that quantum computations take place in microtubules orchestrated by the inputs of synapse via maps. Hence, the theory is often known as Orch OR for orchestrated objective reduction. The computations are suggested to persist for 25 milliseconds, which would link them to the 40 Hz gamma synchrony viewed as a correlate of consciousness even in more mainstream theories. The computations are terminated by objective reduction. It is proposed that in the dendrites, the tubulin subunits of microtubules interact by dipole coupling, so as process information, the tubulin conformation is governed by quantum London forces, so the tubulins can exist as quantum superpositions of different conformations. In superposition, the tubulin would be qubits in a quantum computer, computing by means of non-local entanglement with other tubulin qubits. This entanglement would not just be with the tubulins of the same microtubule, but other microtubules in the same dendrite, and other dendrites connected by a gap junction. Neurons connected by gap junctions can be viewed as a single hyperneuron, and the hyperneuron can be seen as conventional neuron assembly. The dendritic interiors alternate between two states as a result of the polymerization of actin protein. In the depolymerized form, the interior of the neuron is aqueous in the microtubule signal and process information. Classically, there are synaptic inputs to the microtubules during this phase. When actin polymerizes, the interior of the dendrite becomes quasi-solid and of gelatinous, and water near to the proteins becomes ordered as a result of the actin gelatin. Debye layers of counterions may also shield the microtubules due to the charged C-terminals tails of the tubulins. This is suggested to make the microtubules sufficiently isolated from the environment for quantum superposition to occur in the tubulins. The geometry of the quantum computer lattice could be formed so as to be resistant to decoherence. Microtubules are suggested to have a structure which is particularly suitable for error correction. Coherent pumping of energy and quantum error correction may thus help to prevent decoherence. Quantum error correction involves a code that can detect and correct decoherence in a quantum system. Hameroff claims to refute Tegmark's attempt to disprove the Penrose-Hameroff model. This is significant as Tegmark's criticism of Orch OR has been widely accepted as a completely satisfactory dismissal of the theory, and responses to Tegmark are habitually ignored. Tegmark calculated microtubule decoherence time as being 10 to the negative 13 seconds, which would certainly be much too short for any neural activity. However, he worked on the basis of his own model for quantum activity in microtubules, which was never proposed by Hameroff or anyone else, basing his calculation on a 24 nanometer separation of solutions from themselves along the microtubules, whereas Orch OR proposes the superposition separation distance 6 orders of magnitude smaller. For some reason, Tegmark did not choose to address the Penrose-Hameroff model. This invalidates his particular approach, whatever the truth about the decoherence, but somehow it has not prevented his work from being quoted as an absolutely reliable refutation of Orch OR. A recent update on the Orch OR model, a recent review and update of the 20-year-old theory of consciousness published in Physics of Life Review 2013 persists to claim that consciousness derives from deeper level, finer scale activities inside brain neurons. The recent discovery of quantum vibrations in microtubules inside brain neurons corroborates this theory, according to review authors Stuart Hameroff and Roger Penrose. The groundbreaking article and some of the accompanying comments are partly cited and summarized in the following. Hameroff and Penrose suggested that the EEG rhythms also derive from deeper level microtubule vibrations, and that from a practical standpoint, treating brain microtubule vibrations could benefit a host of mental, neurological, and cognitive conditions. Orch OR was harshly criticized from its inception, as the brain was considered too warm, wet, and noisy for seemingly delicate quantum processes. However, evidence has now shown warm quantum coherence in plant photosynthesis, bird brain navigation, our sense of smell, and brain microtubules. The recent discovery of warm temperature quantum vibrations in microtubules inside brain neurons in the research group led by Anirban Bandapade 2011 at the National Institute of Material Sciences in Japan corroborates the pair's theory and suggests that EEG rhythms also derive from deeper level microtubule vibrations. In addition, work from the laboratory at Emerson and Eckenhorf at the University of Pennsylvania suggest that anesthesia, which selectively erases consciousness while sparing non-conscious brain activity, acts via microtubules and brain neurons. The origin of the consciousness reflects our place in the universe, the nature of our existence. Did consciousness evolve from complex computations among brain neurons, as most scientists assert, or has consciousness in some sense been here all along, as spiritual approaches maintain? Ask Hameroff and Penrose in their current review. This opens a potential Pandora's box, but our theory accommodates both these views, suggesting consciousness derives from quantum vibrations and microtubules, protein polymers inside brain neurons, which govern neuronal and synaptic function and connect brain processes to self-organizing processes in the fine-scale proto-consciousness quantum structure of reality. After 20 years of skeptical criticism, the evidence now clearly supports OR, continue Hameroff and Penrose. Our new paper updates the evidence, clarifies OR quantum bits, or qubits, as helical pathways in microtubule lattices, rebuts critics and reviews 20 testable predictions that OR published in 1998. Of these, 6 are confirmed, but none refuted. An important new facet of the theory is introduced. Microtubule quantum vibrations appear to interface and produce much slower EEG beat frequencies. Despite a century of clinical use, the underlying origins of EEG rhythms have remained a mystery. Clinical trials of brief brain stimulation aimed at microtubule resonance with megahertz mechanical vibrations using transcranial ultrasound have shown reported improvements in mood and may prove useful against Alzheimer's disease and brain injury in the future. Lead author Stuart Hameroff concludes, OR is the most rigorous, comprehensive, and successfully tested theory of consciousness ever put forth. From a practical standpoint, treating brain microtubule vibrations could benefit a host of mental, neurological, and cognitive conditions. The review was accompanied by 8 commentaries from outside authorities, including an Australian group of OR arch skeptics. To all, Hameroff and Penrose respond robustly. They will engage skeptics in a debate on the nature of consciousness, and Bandyopadhyay and his team will couple microtubule vibrations from active neurons to play Indian musical instruments. Consciousness depends on harmonic vibrations of microtubules inside neurons, similar to certain kinds of Indian music, but unlike Western music, which is harmonic. Hameroff explained that consciousness depends on biologically orchestrated coherent quantum processes and collections of microtubules with brain neurons, that these quantum processes correlate with and regulate neuron synaptic and membrane activity. The continuous Schrodinger evolution of each process is supposed to terminate in accordance with the specific Dassel-Penrose scheme of objective reduction of the quantum state. The orchestrated OR activity is taken to result in moments of consciousness awareness and or choice. The Dassel-Penrose form of OR is related to the fundamentals of quantum mechanics and space-time geometry. So Orch OR suggests that this is a connection between the brain's biomolecular processes and the basic structure of the universe. The authors recently reviewed the Orch OR in light of criticisms and developments in quantum biology, neuroscience, physics, and cosmology. The authors introduced novel suggestions of beat frequencies of faster microtubule vibrations as a possible source of observed electroencephalographic EEG correlates of consciousness. They conclude that the consciousness plays an intrinsic role in the universe. The group of Bandyopadhyay 2011 has indeed discovered conductive resonance in a single microtubules that are observed when there is an applied alternative current at specific frequencies in gigahertz, megahertz, and kilohertz ranges. Electron dipole shifts do have some tiny effect on nuclear positions via change movements and Mossbauer recall. A shift of 1 nanometer in electron position might move a nearby carbon nucleus a few femtometers, roughly its diameter. The effect of an electron spinning magnetic dipoles on nuclear location is less clear. Recent OR publications have cast tubulin bits as coherent entangled dipole states acting collectively among electron clouds of aromatic amino acid rings with only femtometer conformational change due to nuclear displacement. As it turns out, femtometer displacement might be sufficient for Orch OR Dassel-Penrose objective reduction in a particular proposal for an extension of current quantum mechanics, taking the bridge between quantum and classical level physics as quantum gravitational phenomenon. This is in contrast with the various conventional viewpoints whereby this bridge is claimed to result somehow from environmental decoherence, or from observation by a conscious observer, or from choice between alternative worlds, or some other interpretation of how the classical world of one actual alternative may be taken to arise out of a fundamental quantum superimposed ingredients. Early and current version of the OR cubic. Early and current versions of the OR qubit, schematic cartoon versions of OR tubulin protein qubit used in OR publications mainly from 1996 to 98. On the left, tubulin oscillates between two states with 1 nanometer conformational flexing. On the right, both states exist in quantum superposition. Irrespective of the schematic cartoon, the 1 nanometer displacement has never been implemented in OR calculations. The states are shown to correlate with electron locations in two adjacent phenyl or indole resonance rings in nonpolar hydrophobic. Schematic cartoon version of the OR qubit developed since 2002. Following identification of tubulin structure by electron crystallography, each tubulin is shown to have 9 rings representing 32 actual phenyl or indole rings per tubulin, with coupled oscillating London forces dipole orientations among rings traversing quantum channels, aligning with rings in adjacent tubulins in helical pathways through microtubule lattices. On the right, superposition of alternative tubulin in helical pathways dipole states. There's no conformational flexing. Mechanical displacement occurs at the femtometer level of tubulin atomic nuclei. Reimers et al. Continually and exclusively criticize the obsolete non-independent version on the left and ignore the actual Orch OR dipole pathway qubit version on the right. The Dassey-Penrose version of OR involves a different interpretation of the term quantum gravity from what is usual. Current ideas of quantum gravity, like Smolin, normally refers instead to some sort of physical scheme that is to be formulated within the bounds of standard quantum field theory, although no particular such theory among the multitude that has so far been forward has gained anything approaching universal acceptance, nor has any of them found a fully consistent, satisfactory formulation. OR here refers to alternative viewpoint that standard quantum field theory is not the final answer, and that the reduction of the quantum state collapse the wave function that is adopted in the standard quantum mechanics is an actual physical process which is part of the conventional unitary formalism of quantum theory or quantum field theory. In the Dassey-Penrose version of OR, the reduction of the quantum state does not arise in some kind of convenient or effective consequence of environmental decoherence, as the conventional formalism would seem to demand, but is instead taken to be one of the consequences of melding together the principles of Einstein's general relativity with those of conventional unitary quantum formalization. And this demands a departure from the strict rules. According to the OR viewpoint, any quantum measurement whereby the quantum superimposed alternative produced in accordance with the formalism becomes reduced to a single actual occurrence is a real objective physical process and is taken from the result of the mass displacement between the alternatives being sufficient in gravitational terms for the superposition to become unstable. It is helpful to have a conceptual picture of the quantum superposition in gravitational context. According to modern accepted physical theories, reality is rooted in 3-dimensional space and 1-dimensional time, combined together in a 4-dimensional spacetime. This spacetime is slightly curved in accordance with Einstein's general theory of relativity, in a way which encodes the gravitational fields of all distributions of mass density. Each different choice of mass density affects a space-time curvature in a different, albeit very tiny way. This is the standard picture according to classical physics. On the other hand, when quantum systems have been considered by physicists, this mass-induced tiny curvature in the structure of space-time has been almost invariably ignored, gravitational effects having been assumed to be totally insignificant for normal problems in which quantum theory is important. Surprisingly, as it may seem, however, such tiny differences in space-time structure can have large effects, for they entail subtle but fundamental influences on the very rules of quantum mechanics. The initial part of each space-time is at the upper left of each individual space-time diagram, and so the bifurcating space-time diagram on the right, moving downward and rightward, illustrate two alternative mass distributions evolving at time, their space-time curvature separation increasing mechanically so as OR has not taken place. The physical reality of the situation as provided by the evolving wave function is being illustrated as an actual superposition of these two slightly differing space-time manifolds. The OR process is considered to occur when quantum superpositions between such slightly different spacetimes take place, differing from one another by an integration space-time measure, which compares with the fundamental and extremely tiny Planck scale of space-time geometry as marked above. This is a 4-volume Planck measure involving both space and time. So we find the time measure would be particularly tiny when the space-time difference measure is relatively large, as with Schrodinger's hypothetical cat. But for extremely tiny space difference measures, the time measure might be fairly long. For example, an isolated electron in a superposed state, very low EG might reach OR threshold only after thousands of years or more, whereas Schrodinger's cat would be put into superposition of life and death. This threshold could be reached in far less than the Planck time. As superposition curvature E reaches threshold, OR occurs, and one particle location curvature is selected and becomes classical. The others cease to exist. In the situations under consideration here, where we expect a conscious brain to be at a very far from zero temperature, and because technological quantum computers require zero temperature, it is very reasonable to question quantum brain activities. Nevertheless, it is not now well known that superconductivity and other large-scale quantum effects can actually occur at temperatures very far from absolute zero. Indeed, biology appears to have evolved thermal mechanisms to promote quantum coherence. Oyoung and Oshalom 2003 showed that quantum spin transfer through phenyl ring pi orbital resonance clouds, the same as those protein hydrophobic regions, are enhanced at increasingly warm temperatures. Spin flip currents through microtubule pathways may be directly analogous. In the past 6 years, evidence has accumulated that plants routinely use quantum coherent electron transport at ambient temperatures in photosynthesis. Photons are absorbed in one region of photosynthetic protein complex, and their energy is conveyed by electronic excitations through the protein to another region to be converted into chemical energy to make food. In this transfer, electrons utilize multiple pathways simultaneously through pi electron clouds in a series of chromophores analogous to hydrophobic regions named space nanometers apart, maximizing efficiency via so-called exciton hopping. Chromophores and photosynthesis proteins appear to enable electron quantum conductance precisely like aromatic rings are proposed in Orch OR to function in tubulin microtubules. Quantum conductance through photosynthesis protein is enhanced by mechanical vibration, and microtubules appear to have their own set of mechanical vibrations in megahertz as suggested by Sahu 2013. Megahertz mechanical vibrations, ultrasound, and brief low-intensity subthermal ultrasound administered through the skull and the brain modulates electrophysiology, behavior, and effect, improve mood in patients suffering from chronic pain, perhaps by direct excitation of brain microtubules. Further research has shown warm quantum effects in bird brain navigation, ion channels, sense of smell, DNA, protein folding, biological water. What about quantum effects in microtubules? In the 1980s and 90s, theoretical models predicted Frohlich gigahertz coherence and ferroelectric effects in microtubules. In 2001-4, coherent megahertz emissions were detected from living cells and ascribed to microtubule dynamics by the group of Jiri Pokorny in Prague. Beginning 2009, Anibir Bandapati and colleagues of the National Institute of Material Science in Japan were able to use nanotechnology to address electronic and optical properties of individual microtubules. The group has made a series of remarkable discoveries suggesting that quantum effects do occur in microtubules at biological temperatures. First, they found that electronic conductance along microtubules, normally extremely good insulators, become exceedingly high, approaching quantum conductance at certain specific resonance frequencies of applied alternating current stimulation. The resonance occurred in gigahertz, megahertz, and kilohertz ranges, and particularly prominent in low megahertz. Conductances induced by specific AC frequencies appear to follow several types of pathways through the microtubule, helical, linear along the microtubule axis, and blanket-like around the entire microtubule surface. Second, using various techniques, the Bandapati group also determined AC conductance through 25 nanometer wide microtubules is greater than through the 4 nanometer wide tubulins, indicating cooperative, possibly quantum coherent effects throughout the microtubule, and that the electronic properties of microtubules are programmed within each tubulin. The result also showed that conductance increased with microtubule length, indicative of quantum mechanism, conscious event by quantum computing in one of the vast number of microtubules. Tentatively proposed picture of a conscious event by quantum computing in one of the vast number of microtubules all acting coherently so that there is a sufficient mass displacement for Orch OR to take place. Tubulins in a classical dipole state, yellow or blue, or quantum superposition of both dipole states. Quantum in gray, quantum superposition computation involves during integration phases 1 to 3 in the integrate in fire brain neurons, increasing quantum superposition, e.g., gray tubulins, until threshold is met, at which time a conscious moment occurs, and tubulin states are selected which regulate firing and control conscious behavior. In the middle, corresponding alternative superimposed spacetime curvatures, reaching the threshold at the moment OR and selecting one spacetime curvature. In the bottom schematic of a conscious Orch OR event, showing U-like evolution of quantum superposition, increasing e.g., until OR threshold is met and conscious moment occurs. The resonance conductance, bond-to-body coherence through tubulins and microtubules is consistent with the intratubulin aromatic ring pathways, which can support Orch OR quantum dipoles, and which anesthetics bind apparently to selectively erase consciousness. Bond-to-body's experiments do seem to provide clear evidence for coherent microtubule quantum states at brain temperature. This said, solid scientific evidence, microtubules and the rest, is not yet completely convincing, and one is left with a desire to contribute to the whole intellectual construction in order not to leave its present state. Anyhow, certain parts of the mosaic are particularly appealing. The fact, for instance, that anesthesia gas exerts their effects on consciousness, and that actual evidence from genomics and proteomics point to the anesthetic action in microtubules. As Faraday said, it is always better to have a partial vision of the facts rather than having none. Some could, on the contrary, be fully convinced of the existence and function of objective reductions of the quantum states occurring in and orchestrated by biological structures. Of these, microtubules would represent the most efficient evolutionary winning examples, consciousness being the most visible of the non-epiphenomenal phenotypes. As a novel suggestion relative to the previous studies, beat frequencies are introduced by Hameroff and Penrose as a possible source of the observed electro e.g. correlates of consciousness. Introducing quantum physics into the realm of biology entails another major positive aspect. Room is made for Darwinianism and chance and necessity reason. Biological structures as microtubules evolved as well with Darwinian logic, which occurred to cause objective reduction in quantum state. Once Darwin enters the scene, everything becomes possible. Our mind provides the a posterior verification for a deeper look at the concept. The reader is referred to the elaboration of the terms Erignus and Erignen by Martin Heidegger. The basic Hameroff and Penrose assumption would be in the case of objectively become of paramount importance. The Hameroff-Penrose form of orchestrated objective reduction is related to the fundamentals of quantum mechanics and space-time geometry, hence the connection between the basic structure of the universe and the biomolecular processes. Relating these effects to neurons might appear an unjustified self-inflicted limitation, and in this perspective, the general conclusion should not be avoided. Consciousness is a property and a manifestation of life. Life is universal in principle, thus consciousness is in principle universal. A note of caution, Roger Penrose himself recently said, I do not see why we should take the quantum mechanics as a sacrosanct. I think there's going to be something else which replaces it. These words, if they can be considered as not being out of context, find their explanation in the incompleteness of quantum theory. This awareness of the incompleteness is at the very basis of the Orch OR theory, and it's reappearing throughout this important essay. Okay, God bless. So, Dave, Orfeo, I'll probably wrap this up in maybe 15 more minutes. It's been a long time, but finally appearing the end. Let me pour myself a drink. I underestimated how long this article is, but I think it's important. I'm reading it all out, and hopefully a few people listening will gain from it, and you're reading along and studying it, and you'll have a thorough overview of quantum consciousness and all the major theories, and went very in depth into Penrose Hameroff objective, orchestrated objective reduction. But we're not finished, and this is just an overview. So the work never finishes. Hiroomi, Umezawa, and the Herbert Frohlich quantum brain dynamics. Basic concept of quantum brain dynamics. QBD is that the electrical dipoles and the water molecules of the brain constitute a cortical field. The quantum in this field are described as corticons. The field interacts with quantum coherent waves propagating along the neuronal networks. There's more than one view within quantum brain dynamics, QBD, as to how the system supports or instantiates consciousness. The ideas behind QBD derived originally from the physicist Hiroomi, Umezawa, and Herbert Frohlich in the 1960s. In the last 20 years, these ideas have been elaborated and given greater prominence from the combined efforts of the Japanese physicist Marijibu and Kunio Yasu and the Italian physicist Giuseppe Vitiello. Ian Stuart Hameroff and Takahashi proposed the idea of a cortical field in the brain. Water comprises 70% of the brain, and QBD proposes that rather than providing a passive background, water could be an active player in brain processes. Water molecules have a constant electric dipole and are considered in QBD to be capable of interacting with waves generated by biomolecules that are also electrical dipoles. In QBD, the totality of the water molecule in the brain is viewed as the best candidate for the cortical field, with the water electrical dipoles binding both to one another and to biomolecules in the neuronal network. There are also suggested to be long-range waves within the cortical field. The quantum of the cortical field are given the name corticons, and Jibu and Yasu's version of the theory, the interaction between the cortical field and the neuronal network, particularly the dendritic part of the network, is the basis of consciousness. The other half of the theory refers to biomolecules propagating through the neural network, an idea deriving from the field of Frohlich. Frohlich argued that it was not clear how order was sustained in living systems, given the likely disrupting effect of the fluctuations in biochemical processes. His idea relates mainly to the ordering of neuronal networks on which the proposed cortical network of Umezawa is proposed to act. Frohlich saw the electrical potential across the cell membrane as the macroscopical observable of an underlying quantum order. Frohlich studies claim to show that with oscillating electrical charges, as in thermal bath, a large number of quantum may become condensed into a single state, known as a Bose condensate, allowing long-range correlations among the dipoles involved. He also proposed that biomolecules with a high electric dipole moment line up along the actin filaments, and the electric dipole oscillations propagate along these filaments in the form of quantum coherent waves. There is some support for these ideas in the form of experimental confirmation that biomolecules have high electric dipole moments and have a periodic oscillation. Vitiello argues with Frohlich in arguing that living systems constitute ordered chains of chemical reactions, which could normally be expected to collapse in the random chemical environment of biological tissues. In Vitiello's view, stable ordering comes from the quantum level, but this is described by quantum field theory rather than quantum mechanics. He also claims that the folding of protein, which is fundamental to the activity of cells, cannot be described by classical physics, but could be quantum ordered. Vitiello provides citations which he feels support a quantum dynamical view of biological tissues, notably studies of radiation effects on cell growth, electromagnetic fields, and stress on dynamic response to external stimuli, or on nonlinear tunneling, on coherent nuclear motion in membrane proteins, on optical coherence in biological systems, on weak radiation fields and biological systems, by and on energy transfer via solutions and coherent excitations. QBD proposes that the cortical field not only interacts with, but is also to a good extent controls the neuronal network. It suggests that the biomolecular waves propagate along the actin filaments, an important part of the cytoskeleton, particularly in the vicinity of the cell membrane and dendritic spines. The waves derive energy from ATP molecules stored in the membrane, and these in turn are controlled by calcium ions. These waves are also suggested to control the action of ion channels, which are crucial in the transmission of signals to the synapses. The neuronal membrane is further suggested to act as a Josephson junction providing insulation between two layers of superconductivity. The superconductivity current across the membrane can be controlled by electrical potential across the same membrane. Vitiello also discusses the question of quantum decoherence. He claims that QBD only requires quantum oscillations to last 10 to 14 picoseconds, which should be much shorter than the period required for decoherence. In common with Stuart Hameroff, he additionally argues that ordered water around protein molecules may shield them from the surrounding thermal bath. A decisive further step in developing the approach has been achieved by taking dissipation into account. Dissipation is possible when the interaction of a system with its environment is considered. Vitiello describes how the system-environment interaction causes a doubling of the collective modes of the system and the environment. This yields infinitely many different coded vacuum states, offering the possibility of many memory contents without overprinting. Finally, dissipation generates a genuine arrow of time for the system, and its interaction with the environment induces entanglement. In a recent contribution, Pest and Vitiello have addressed additional effects of chaos and quantum noise. Jibu and Yasu appear to see consciousness as simply a function of the interaction of the corticons, the energy quantum, which are produced to arise in the cortical field, with the biomolecular waves of the neuronal network. Vitiello, while thinking in terms of much of the same quantum systems as Jibu and Yasu, proposes that these quantum states produce two poles. First, a subjective representation of the external world, and secondly, a self which opens itself to this representation of the external world. According to Vitiello's version of the theory, consciousness is not strictly speaking in either the self or the external representation, but between the two, in the opening of one to the other. The concept derives from the Japanese physicist Hiroomi Umezawa, who speculated that understanding the process of memory in the brain would involve quantum field theory. This led onto the idea that understanding consciousness would also involve quantum field theory. The first 4 chapters of their book in 1993 provided standard background to quantum theory and neuroscience. Those without some grounding would be better advised to look at the more standard textbooks or popularizations, as the style of the book is generally difficult and unnecessarily repetitive. The first 4 chapters of the book deal with quantum theory. For those not familiar with this, there are many much more comprehensible descriptions. This is followed by some descriptive passages on the brain, which is again better described elsewhere. Getting beyond these introductory stages, the authors make the same point as others in stressing that the estrangement between physics, where fundamental new views of nature emerged during the last 100 years, and neuroscience, which has remained largely wedded to 19th century physics. In particular, physics has tended to think dynamically in terms of controlled changes. Physics deals primarily with the inanimate, but the concepts of dynamics can be applied to living organisms as they also undergo controlled changes. The authors suggest that the functions of the cortex might be better understood through the dendritic network by which information enters cells. They stress that many neurons in the cortex do not have axons but only dendroids. They think that the conventional processing system described in the axon neurotransmitter dendroid system may overlook other networks in the brain. Neurons without axons are the majority of the cortex, and the authors see these as the likely basis of consciousness. Synaptic electron tunneling. The electron jumps over calcium ion tunnels throughout the cleft. This thematic representation of the synapse and synaptic cleft within the element of quantum tunneling electrons and dendritic network. The authors discuss the dendritic network at length. They point out that much more sophisticated than the axonal network, the dendritic membrane comprises biomolecules with electrical dipoles. The positive poles of the membranes are aligned to the inner surface and the negative poles to the outer surface. The negative poles on the outer surface attract positive ions, while the positive poles on the inner surface attract negative ions. The region where these interactions occurred are called debut layers. The dendrites of several neurons are often entangled in a network. Chemical synapses are located on the tips of dendritic spines, and there are M phases of the dendritic membranes. In such processes, even quantum tunneling may play a significant role. Since the 1970s, Evan Harris Walker has proposed that the quantum tunneling of electrons would take place across junctions like neurons. Stuart Hameroff says gap junctions enable quantum tunneling among dendrites. According to the principle of modern physics, if a particle such as an electron encounters a barrier such as a synaptic junction, there is a finite probability that the particle will be found on the other side. From this point of view of Bohm's pilot wave quantum theory, Peter Holland says that quantum tunneling is explained because the effective barrier potential is not the classical barrier potential, but is the quantum potential. From the many worlds point of view, quantum tunneling means that the electron is in a superposition of position states, some of which are on one side of the junction and some of which are on the other. Therefore, quantum tunneling can allow quantum superposition states to extend from neuron to neuron across gap junctions. This is an experimental confirmation that biomolecules of high electric dipole moments have a periodic oscillation. The author suggests that the oscillations are crucial to the functioning of the brain. This can be called wave cybernetics because the wave or biomolecule oscillation is seen as the controlling factor in the brain. Frohlich proposed that a theory where biomolecules with high electric dipole moment line up along the actin filaments immediately below the cell membrane, while electric dipole oscillations propagate along each filament as coherent waves. These are maintained by electrons trapped in the moving along the protein molecules. This is known as the Frohlich wave. These waves exchange energy with the electromagnetic field. Proposed Stuart Hameroff and Takahashi 1978 proposed the idea of a cortical field. This interacts with the macroscopic dynamics of the main neural network, which in turn transmits signals to the body tissues. The filament strings found in the cells also extend outside the cell, forming an extracellular matrix that is also linked to cell membrane. So the membrane proteins are linked both to the cytoskeleton and the extracellular matrix. The authors proposed that the Frohlich waves propagate along the filamentous strings. The waves are produced by energy stored in ATP molecules at membrane protein sites, which are in turn controlled by calcium ions. The waves also affect the operation of ion channels, which control neural impulses. The authors suggest that the structure can give rise to macroscopic quantum phenomenon similar to superconductivity. They also regard the cell membrane as an insulating layer between two areas of superconductivity, otherwise known as the Josephson junction. This means that superconductivity current across the Josephson junction can be controlled by electric potential differences in the insulating layer. The author suggests that this quantum activity may facilitate the functioning of the brain and in particular an interface between the proposed cortical field and the neural networks. The cortical field is proposed to contain energy quantum behaving as particles, which the author calls corticons. Corticons are suggested to exist everywhere in the cerebral cortex. The interface between the cortical field and the neural network take place in the waves propagating along the filamentous strings in the cytoskeleton and the extracellular matrix. The authors emphasize the nature and importance of water within the brain. They suggest that water is not just a background substance, but is an active component in cell assemblies. This idea lies behind the original concept of the cortical field and corticons. The water molecule has a constant electrical dipole. It also has a symmetrical form that is invariant under reflection. The molecule rotates around its symmetry axis, which is the electrical dipole. Thus, the molecules in quantum mechanical spinning top, which interacts with the fields generated by biomolecules. The totality of water molecules in the brain is seen as the best candidate for the sought-for cortical field. In water, one side of the molecule becomes negatively charged and one side positively charged, creating an electric dipole. This is an attraction between molecules known as hydrogen bonding. The attraction is both between water molecules and between water molecules and other molecules with electrical dipoles. Biomolecules such as proteins have constant electrical dipoles and connect to water molecules. The cortical field is identical with the water rotational field created by the spinning dipoles of the water molecules. The field on the cytoskeleton and extracellular matrix is proposed to be a Bose field, and the interaction between the Bose field and the corticons and the cortical field is seen as the basis of consciousness. Corticons are identified with the energy quantum of the water rotational field in the brain. The corticons interact with each other by emitting and absorbing the exchange bosons of the Bose field and are themselves the energy quantum of the water rotational field. The water rotational field is a dipole field and therefore interacts with the electromagnetic field. There are also suggested to be a long-range correlation waves in the water rotational field in the brain. The brain structure described here are thought to be sensitive and to modify themselves in responses to information coming into the brain. The combined dynamics of the cortical field and electromagnetic field comprise what the authors describe as quantum brain dynamics. The dynamics of the corticons is thought to be capable of controlling the dendritic and neural networks. The authors think that the creation and annihilation of corticons in the QBD is what is called consciousness. Unfortunately, the authors do not explain why they think this, and therefore, like more mainstream theories of consciousness, the actual consciousness seems to be created by fiat. There's no more apparent reason why consciousness should arise from this physical interaction than from the physical interaction of electron potentials and chemical in the synapses. The authors could have suggested that consciousness was a fundamental property of photons or proposed quarticons or of particular fields, but they do not do this. Johnjoe McFadden, electromagnetic fields in the brain. McFadden starts by stating that the synchronous firing of brain correlates with the awareness and perception, indicating that disturbances in the brain electromagnetic field are also correlate with these. The field is a representation of neuronal information, and its dynamics could be seen as a correlate of consciousness. McFadden views this field as the physical substrate of consciousness. Popper and Liebate have both suggested that consciousness might derive from an overarching field that could integrate the processing of neurons, but they did not think that this could be any known physical field. At the same time, there has been considerable interest in the synchronous firing of neurons. Awareness has been shown to correlate with the synchrony of firing in the 40 to 80 hertz range, and this may bind together neurons involved in different aspects of the same visual perception, thus creating the unity of consciousness. The brain's electromagnetic field is induced by neural firing and also the movement of ions involved in the fluctuation of electrical potential along the cell membrane. The structure of the cortex tends to amplify the induced field. Experiments in the olfactory bulb have demonstrated EEG activity in response to sensory stimuli, information about the stimuli related to the spatial pattern of the EEG amplitude. The author concludes that the brain contains a highly structured extracellular magnetic field. The field is weak, with the transmembrane fields being about 3,000 times stronger. It is suggested that neurotransmission through gap junctions may be voltage dependent and therefore sensitive to local fields. However, McFadden prefers to concentrate on the voltage gated ion channels in the cell membranes because their role is better understood. Synchronous firing is thought to be due to a large number of spatially distributed neurons. It is thought that many millions of neurons could be influenced by such firing. McFadden claims evidence for neural communication to be electromagnetic field, the electromagnetic field theory of consciousness, as part of an integral electromagnetic spectrum. The medical use of transcranial magnetic stimulation is taken to indicate the sensitivity of the brain to weak electromagnetic fields, and is seen this has impacts on behavior. It is argued to impact neuronal computation and neuronal function. Even when fields are weaker than the surrounding noise, they can modulate neurons. The brain's electromagnetic field is argued to hold the same information as the neural firing patterns. The widespread of the electromagnetic field would help to explain the unity of consciousness. Clusters of neurons in the visual cortex have been shown to fire in synchrony in response to particular stimuli. With insects, destruction and synchronous firings have been shown to reduce the ability to discriminate between stimuli. There is indirect evidence for the correlation between synchronous firing and attention awareness in humans. The olfactory system of rabbits shows that the sensory information is encoded in spatial patterns of the EEG and therefore of the electromagnetic field. This correlation also reflected what a particular smell meant to the rabbit when it had been trained to associate particular things with a smell. This suggested that the shape of the electromagnetic field could be related to perception, meaning this is taken to suggest that consciousness is related to the electromagnetic field where there is habituation with the process and therefore less conscious activity. There is a reduction in synchronous firing, so loss of awareness correlates with reduced disturbance in the brain's electromagnetic field. The theory predicts that only activity that acts on the motor neurons is conscious. This is testable, although there is no direct evidence. The EEG shows that activity increases during creative thinking, declines with sleep, but revives with REM dreaming. So the amount of conscious activity correlates with the amount of electromagnetic activity. The high conductivity of the cerebral fluid in the brain ventricles makes the brain into a kind of Faraday cage, insulating it from external electric fields. However, it is much easier for magnetic fields to penetrate the brain and other tissues. Moving magnetic fields, such as those used in TMS, do produce effects on the brain. McFadden, the function of consciousness. McFadden sides with those who argue that consciousness must have a function or evolution would not have selected for it. Fields effect that had an advantageous effect on the performance of ion channels would have been selected for. McFadden thinks that there is information transfer between neurons During synchronous firing, he proposes that neural circuits involved in consciousness and unconscious activity differ in their sensitivity to the electromagnetic field. The consciousness will is claimed to be our experience of the electromagnetic field. He thinks that consciousness is not actually the electromagnetic field, but its ability to transmit information to neurons. He also points out the difficulty of trying to perform two conscious tasks or a conscious and unconscious task at the same time. The two interfere with each other, while unconscious multitasking is possible. Consciousness is required for laying down of long-term memories for the most learning. The semi-field theory conceives that the electromagnetic field in the brain fine-tunes the probability of neural firing. The affected neurons may be part of larger connected assemblies, and this leads to memory and learning. In stimulated networks of non-synaptical neuron interactions via the electromagnetic field, and also gap junctions enhance learning. Modulation of long-term potentiation by electromagnetic fields also has been demonstrated in vitro in rat hippocampal slices. McFadden and free will. The author claims that free will is the subjective experience of the influence of the semifield on neurons. However, the influence of the semifield is seen as entirely deterministic. The fluctuations in the field that are capable of modulating the firing of neurons would all be generated by charging patterns of electrical activity, while the neurons themselves induce the field. The author admits that there might be some element of random quantum fluctuations in the field, but this randomness is unsuitable for producing free will. The author, in common with others in consciousness studies, tries to have it both ways at this point. The functioning of the brain is claimed to be entirely deterministic, but something called will is active in driving our conscious actions. This appears to be a clear contradiction, since the whole idea of will is an agent which initiates something of its own accord. The semi-theory is trying to provide a plausible explanation of consciousness. The author could have said that consciousness was a fundamental property of electric charge, or individual charged particle, or the photons that intermediate it, thus making it a primitive or brute fact of the universe. But he does not do this. He says that our conscious will is our experience of this influence of the semi-field. This seems to raise a host of questions and contradictions. If the semi-field isn't conscious itself, who or what is experience its influence? To suggest a dualistic, non-physical entity that experiences the action of the field. Even if we are happy with the concept, it is not clear why this particular set of electromagnetic fields should produce this experience for this entity. Like many before, McFadden suddenly declares by fiat that one particular part of otherwise ordinary material, the brain, produces consciousness. Again, it is reasonable to say that evolution selected for a particular type of field that could fine-tune the neurons, but the additional production of a feeling of free will, which is false, has no demonstrable value. Gustav Bernroider, ion channel coherence. Ion channels are a crucial component of the axonal spiking synaptic firing model of neuronal signaling and information processing. The axonal signal starts from the body of the neuron and proceeds down an extension called the axon by means of a fluctuation in the difference in electric potential across the membrane that forms the exterior of the axon. The membrane is formed by a double layer of lipids. The ion channel consists of a protein molecules inserted through the lipid bilayer. The axon fires when the sodium ions flow through one set of ion channels and subsequently returns to its resting state when potassium ions flow through another set of ion channels. The process continues down the length of the axon until it reaches the synapse, which allows it to fire and thus communicate with the other neurons. Ion channels are thus a key mechanisms in the brain signaling and information processing. Quantum coherence in the potassium ion channel. The potassium channel structure that protects the potassium ion from decoherence and the flow of quantum information through the entangled series of channels. Bernroider and Roy based this theory on recent studies of ion channels. They've been made possible by advances in high-resolution atomic level spectroscopy and accompanying molecular dynamic simulations. In this work, they draw particularly on the work of the McKinnon group and the studies of potassium channel, especially the closed state of the channel. The functioning of the potassium channel occurs in two stages. Finally, the selection of the potassium ions in preference to any other species of ion. Second, voltage gating that controls the flow of these favored potassium ions. The author says that the traditional understanding of both functions has been altered by the recent studies. In the closed state, the channel is now seen to stabilize 3 potassium ions, 2 in the permeation filter of the ion channel and 1 in the water cavity to the intercellular side of the permeation path. In the case of the ion channel's voltage gating, the electrical charge involved which were previously thought to act independently of the surrounding proteins and lipids, are now seen to be coupled with these proteins and lipid, and thus involved in the gating process. Atomic level spectroscopy has revealed the detailed structure of the potassium channel and its closed gate. The filtered region of the channel has a framework of 5 sets of four oxygen atoms, which are each part of the carboxyl group of amino acid molecules in the surrounding protein. These are referred to as binding pockets involving 8 oxygen atoms in total. Both ions in the channel oscillate between 2 configurations. Bernroider and Roy's calculation lead them to claim that ion permeation can only be understood at the quantum level. Taking this as an initial assumption, they go to ask whether the resulting model of the ion channel can be related to logic states. Their calculation suggests that the potassium ion and the carboxyl atoms of the binding pockets are the 2 quantum entangled subsystems, and they equate this to a quantum computational mapping. The potassium ions that are destined to be expelled from the channel could, in the author's hypothesis, encode information about the state of the oxygen atoms in the axon membrane. In later papers presented in the Quantum Mind Conference, Bernroider proposed that the different ion channels could be non-locally entangled, thus proposing a quantum process over an extended area of the axon. Given the importance of the ion channels in brain functioning, this model would give quantum coherence and non-locality in the axon membrane an integral role in the brain signaling and information processing. Further, this Bernroider and Roy have pointed out similarity between the structure of the potassium ion channel and some recent proposals for building quantum computers in which ions are held in microscopic traps. The authors argue that their model is well protected against decoherence, which has always been the most cogent criticism of quantum consciousness proposals. In particular, they claim that Tegmark's calculations do not apply to their model. The authors agree that for ions moving freely in water, Tegmark's coherence time of 10 to the negative 20 seconds would apply. However, they argue that the situation the ions held in the permeation filter of the ion channel is markedly different, with a temperature about half the prevailing level of the brain, and the ions protected from decoherence by the binding pockets in the adjoining water cavity. Bernroider and Roy proposed a quantum information system in the brain that is driven by the entangled ion states in the voltage-gated ion channels. These ion channels situated in the neuron's membrane are a crucial component of the conventional neuroscience description of axon spiking leading to neurotransmitted release in the synapses, the ion channel allowing the influx and outflux of ions from the cell, driving the fluctuation of electron potential along the axon, which in turn provides the necessary signal to the synapse. The author concentrates their attention on the potassium channel, and in particular the configuration of the channel when it is in a closed state. This channel is traditionally seen as having the function of resetting the membrane potential from a firing to a resting state. This is achieved by positively charged potassium ions flowing out of the neuron through the channel. Recent progress in atomic level spectroscopy of the membrane protein that constitute the ion channels and the accompanying molecular dynamic solutions indicate that the organization of the membrane proteins carries the logical coding potency and also implies quantum entanglement within ion channels and possibly also between different ion channels. An increasing number of studies show that proteins surrounding membrane lipids are associated with the probabilistic nature of the gating of the ion channel. Plasma membrane ion channel, crystallographic X-ray determine the structure of potassium channel, and a schematic representation of it showing in the polypeptide unit. The authors draw particularly from the work of McKinnon and his group, notably his crystallographic X-ray work. The study shows that ions are coordinated by carboxyl-based oxygen atom or by water molecules. An ion channel can be either a closed or open state, and in the closed state there are 2 ions in the permeation path that are confined here. The authors regard the closed gate arrangement as the essential feature with regards to their research work. The open gate presents very little resistance to the flow of potassium ions, but the closed gate is a stable ion protein configuration. The ion channel serves 2 functions, selecting potassium ions as the ones that will be given access through the membrane, and then voltage gating the flow of the permitted potassium ions. The authors view recent studies also require change in views both of the ion permutation of the voltage gating process. A charge transfer carried by amino acids is involved in gating processes. In the traditional model, that charges were completely independent, whereas the new model, there's coupling within the lipids that lie in the channel proteins. This view, which came originally from McKinnon, is now supported by other more recent studies. The authors think that the new gating models are more likely to support computational activity that were the traditional models. As mentioned above, 3 potassium atoms would be involved in the ion channel's closed configuration. 2 of these are trapped in the permutation path of the protein. When the ion channel is closed, the filter region of the ion channel is indicated by the recent studies to have 5 binding pockets in the form of 5 sets of carboxyl-related oxygen atoms. Each of the 2 trapped potassium atoms are bound to 8 of the oxygen atoms. Each of them are bound to 2 of the 5 out of the 5 binding pockets. The author's calculations predict that the trapped ions will oscillate many times before the channel reopens, and the calculations also suggest an entanglement state between the potassium ions and the binding oxygen atoms. The structure is seen as being delicately balanced and sensitive to small fluctuations in the external field. This sensitivity is viewed as possibly being able to account for the observed variation in cortical responses. Bernroider's theory might be seen to represent even more of a challenge to conventional neuroscience than the other quantum consciousness theories. This is because it recruits as its basis axon membranes and ion channels, which form a crucial part of the conventional neuroscience model, and then tries to remodel these core structures on the quantum-driven basis. It is hard to deny that if the theory were to become better substantiated, it would produce in neuroscience a revolution of the most profound kind. The essential question was how selectivity could be maintained without compromising conductance. The interaction between ions attracted water molecules and neighboring oxygen atoms is considered to require quantum description. This raises the question of whether quantum effects can propagate in the classic states of proteins. The excess of ions in the pore gates is a relatively slow process, not likely to require quantum processing. However, the selectivity filter can charge its conformation from permissive to non-permissive on a much shorter timescale. It appears that in the conditions of the selectivity filter, the ion's wave function can become highly delocalized over a significant part of the filter region. Synaptic transmission in neural network. Figure here, neurotransmission via neuronal synapse with ion channels and a neuronal network. A new theory of quantum consciousness. Bernroider's theory could potentially be a vehicle for transforming consciousness from the implicate into the explicate order of David Bohm. Bernroider differs from Penrose Hameroff's Orch OR model in his emphasis on the axons and membranes as opposed to the dendrites and cytoskeletons. However, there are similarities between the 2 models in that both of them propose quantum coherence, non-locality, and a subsequent wave function collapse linked to the brain's macroscopic information processing activity. As it stands, Bernroider's proposals only deal with information processing in the brain rather than consciousness as such. However, it appears possible that the wave function collapse in the ion channels might link to Penrose's proposed geometry of spacetime just as readily as the wave function collapse in the cytoskeleton. Bernroider's theory is distinct from all earlier quantum consciousness theories in locating its mechanism and structure that are central to mainstream theories of the brain's information processing and production of consciousness. And future experimentation were to substantiate the Bernroider proposals. This would involve a revolution in neuroscience of the most profound character. Charles King, Cosmology, Consciousness, Chaos, and Fractal Geometry. Charles King favors the approach of Chalmers over the approach of Dennett in looking for the problem of consciousness. He describes Dennett's multiple drafts concept as a description of how verbal reports of internal states are produced, but is lacking in any explanation of how consciousness is achieved. He reminds us of Chalmers' comments that a theory of physics that does not explain consciousness is not a theory of everything. Furthermore, he argues that ultimately our knowledge of objective science is only obtainable via our subjective conscious experiences. He cautions against the common tendency to try to discount quantum uncertainty as something that will be averaged out as a result of the very large number of quantum involved in macroscopic state. In chaos theory, which may well have a role in brain processes, small fluctuations may be inflated into important differences, and quantum uncertainties may be included in these small differences. King goes on to look at the possible uses of quantum computation. He mentions that classical computing has a problem with the potentially unlimited time needed to check a range of possibilities. King favors the transactional approach of the EPR-type non-local quantum correlations and the transactional interpretation of non-local events. When a measurement is made on the entangled particle, it sends a photon back in time to when it and the other entangled particles were emitted, and then forward in time to the second entangled particle. Thus, in the net time taken to send the quantum information about the measurement of the first particle is 0, and the effect of the measurement on the second particle appears to be instantaneous despite the spatial gap between them. The backward travel in time, which looks like an exotic feature, is allowed by the laws of physics as embodied by both Maxwell and Schrodinger's equation. King in 2014 thinks that the transactional interpretation of non-locality can be combined with quantum computing to give space-time anticipating system, and that this may be basic to the way the brain works. He argues that the brain's performance is not particularly impressive in terms of what classical computers are good at, but is impressive in terms of anticipating environmental and behavioral changes. Further citing this article, the transactional interpretation visualizes an exchange particle wave function as the interference of a retarded usual time direction offer wave and time reversal advanced confirmation wave. Time symmetric interactions also occur in quantum field theories where special relativity allows both advanced and retarded solutions because of the energy relation. Virtual photons and electron-positron pairs deflecting an electron in quantum electrodynamics, since the photon is its own antiparticle. A negative energy photon traveling backwards in time is precisely a positive energy one traveling forward. In quantum mechanics, not only are all probability paths traced in the wave function, but past and future are interconnected in a time-symmetric handshaking relationship, so that the final states of the wave particle or entangled state assemble or on absorption are boundary conditions for the interaction, just as the initial states that are created them are. The transactional interpretation of quantum mechanics expresses this relationship neatly in terms of offer waves from the past emitters and confirmation waves from the future absorbers, whose wave interference becomes the single or entangled particles passing them. When entangled pairs are created, each knows instantaneously the state of the other, and if it is found to be a given state of polarization of spin, the other is immediately in the complementary state, no matter how far it is in spacetime. This is the spooky action at distance, which Einstein feared because it violates the local Einsteinian causality in which particles not communicating faster than the speed of light. However, quantum entanglement cannot be used to make classical causal predictions, which would formally anticipate a future event, so the past-future handshaking lasts only as long as the particle or entangled ensemble persist in their wave function. Weak quantum measurement is one way a form of quantum anticipation could arise. Weak quantum measurement is a process where quantum wave function is not irreversibly collapsed by absorbing the particle, but a small deformation is made in the wave function whose effects become apparent later when the particle is eventually absorbed on a photographic plate in a strong quantum measurement. Weak quantum measurements changes the wave function slightly mid-flight because emission and absorption, and hence before the particle meets the future absorber involved in eventual detection. A small change is induced in the wave function by slightly altering its polarization among a given axis. This cannot be used to deduce the state of the given wave particle at the time of measurement because the wave function is only slightly perturbed and is not collapsed or absorbed as in strong measurement, but one can build up a prediction statistically over many repeated quantum of the conditions at the weak point of measurement once post-selection data is assembled after absorption. This suggests that in some sense the future is determining the present, but in a way we can discover conclusively only by many repeats. Focus on a single instance and you are left with an effect with no apparent cause, which one has to put it down to random experimental error. This has led some physicists to suggest that free will exists only in the freedom to choose, not to make post-selection revealing the future. Okay, so God bless. Thanks for sticking with me, anyone who was listening through all of that. Amy. So yeah, this was some really complicated stuff. I'm glad I got through it all. If you want to pop on for a minute, Amy, and just talk about what's going on, or you're streaming, or Dave, if you want to just pop on to say hi. Otherwise, I'm about to call it night. There was some long reading. Duvid spent hours. That was Duvid spent like 3.5 hours reading from there, and like I felt that was pretty important. Yeah, so Michael, thanks for sticking around. So hopefully me and Michael will get together this week, maybe Thursday, 2 o'clock, the regular time, although maybe earlier, to continue our Introduction to Jewish Prayer series. So look forward to that. We had the holiday the last week, and Michael, it was a little bit of drive away from me and his other things, so we missed the last 2 weeks, but we're hoping to continue with that series. So hopefully this week we'll get the 4th installment of our Introduction to Jewish Prayers, and we'll go over most of it word for word in the Hebrew, and hear on Michael how he's progressing. And I put the article, Dave. I really didn't decide, because just week in review, like I try to do some research or cover some stuff related to my research, so I didn't put it out till earlier today. Making the link, and I wasn't sure. I mentioned last week, actually, at the end of the episode, that I showed this article from Dirk Meijer and mentioned that I hope to go over it in more detail, and even to read through the whole thing. So I read a whole bunch of articles last week, and then I mentioned that I might next week I go over this one. So I don't have anything planned for next week, but I'm always doing research and studying. I'm still doing a lot of research into monism, so it's possible next week I'll return to monism, but I'm always researching. So hopefully I'll have something interesting to share next week. Although as of now, no plans. So we'll see what I end up researching in the week, or if any guests or anything you want to message or have something to talk about. So my general area of research, consciousness, science of consciousness, history of science, philosophy of science, spirituality, or then some other topics. So, just week in review keeps me going. I keep on making progress, keep on doing research, sharing my research, trying to network. Unfortunately, my networking is kind of minimal. My viewership is kind of on a low, but I'm always studying, I'm always researching, so I'm always sharing my research. And the people who follow me regularly that might be researching. So I was focusing on this issue because the Science of Consciousness conference was in Italy this week. So the main reason I went, last week and this week, going into details on modern theories of the science of consciousness, was because the Science of Consciousness conference in Italy. And so it could be I'll continue in this Science of Consciousness, or maybe I'll go back to where I was holding, with the advent of molecular biology or the rise of neuroscience. I'm also doing research on the cognitive revolution. I'm trying to put together an essay on the cognitive revolution. So I'm holding in the 1950s in my research, or I could always go back in monism and various things in my research. So, feel free to comment, send me a message, or make recommendations. So that's all I got. I think I'm going to sign off because it's been a long night, and so God bless. Have a great week, Michael. Hopefully we'll see you Thursday or be in contact. And Amy, hope everything's going good for you. Dave, feel free to reach out. And God bless. Have a great week, everyone. Oh, Amy, maybe I should try. I mean, I'll look into the recommendations. I could always be improving my content, and the various methods like keywords or various things. So as of now, I just try to do at least a weekly program. So but I appreciate the feedback and the recommendation. So God bless Dave, Amy, Mike, Orfeo, or Mark Smith, MM, in the chat earlier. Thanks for tuning in, and God bless. Have a great night, great week. See you next week.